Wonderful. I'm super excited to start this meeting here today. I just learned the first Embodied AI workshop here in Nuremberg, so hopefully there will be more in the future. I'm super glad and super excited that so many great colleagues are here and also friends, and we are going to have a workshop about this topic of what we call embodied AI. It's a little bit fuzzy, this term, but we hope that we will clear this up a little bit more and understand a little bit better what is behind all of this, and also where the potential is, and what we can maybe expect from the future regarding this topic that is kind of like flooding the world. And so we have a really great program of experts here. Most of them are actually also here. We'll have, I think, 2 remote presentations, but we are covering diverse topics, including intelligence, computing, hardware, humanoids, and networking, all kinds of super interesting topics related to this field of embodied AI. I'm super glad to have you here for this first workshop. There's a couple of other firsts here that I want to mention. We are a newly founded university. The University of Technology in Nuremberg is only a few years old, 4. And we are the first German AI university. There's another first here. I was the very first professor at this university and setting this university up. I call this the Startup University. And since yesterday, we also do have another first here. We have our very first graduate at this university. She's sitting there at the corner, Rehane. Or let's call her Dr. Rehane. And so she's not allowed to call her like this, but all of you are invited to call her doctor, the very first doctor at this university. So with this, I actually would like to open this workshop, thanking especially our sponsor, Huawei, who made it possible that we are in this spectacular room over here. And we are looking forward to intense discussions. We have experts also from this company here. We have also PhD students from the UTN here, and we have also plenty of guests from other universities here. So I'm hoping that this will be interesting talks, interesting discussions, and maybe also interesting projects coming out of this. With this, I would like to welcome you again, say hi, enjoy this workshop, and let it be as interactive as possible. And we will start with the second introductory or welcome speech by our Vice President for Research and Transfer. It's Alexander Martin. Alexander, he's the representative of the UTN here today and welcoming you for this workshop.
Yeah, it's a little bit higher, so I'm a bit taller. So a very welcome also from my side. As Wolfram has said, I'm the Vice President for Research, Innovation and Entrepreneurship at this new university. And you see here already in the title page our 4 guidelines, so to speak, of our new universities. We want to be interdisciplinary, and interdisciplinary does not only mean within the research itself, but also interdisciplinary beyond the university, being in great cooperations with industry, with the society, trying to address challenging problems of the society of today. We want to be international. That means not only international corporations, but international right from the beginning. We are the first, to come back to this word of Wolfram, we are also the first university who have everything in English. All bachelor study programs are in English. We are the first university in Germany who have everything in English. Also the administration, everything is in English. We want to be digital. That's our 3rd guideline, and digital means also in all phases of the university, in research, in teaching, in administration, and as a sign for this digitalization is our color of the university. You see this green. This green is produced in a way that whenever you print it, it looks worse than if you on the screen. So you should avoid printing stuff, and this comes to our fourth guideline, namely sustainability. We want to be sustainable in all aspects. Concerning printing, of course, is only one aspect, but also in our administration, in doing research, in our mindset, being sustainable. Yeah, these are our four guidelines, and as Wolfram already said, we are actually founded in 2021, so next year we have our first anniversary, the 5th anniversary if you want, so we will celebrate this already. We are the 10th State University of Bavaria, and we are the first university that has been founded after 40 years. So the last one is already 40 years ago that a state university has been founded in Germany. And as I said, our focus is we are an institute of technology, if you want, University of Technology. So our focus is on tech knowledge and innovation by solving global challenges in our society. And as you all know, our society getting more complex and complex. So we always have to integrate all different fields of sciences to address these challenges of tomorrow. And the last one, as I said, we want to establish our four guidelines, namely interdisciplinarity, internationality, digitalization, and sustainability in all aspects of a university. It's learning, it's teaching, it's research, and it's in administration. And to show you some of our landmarks so far, the first, of course, has been our first master program. It's on AI and robotics. It was started in 23, and in the meantime, we have the third cohort starting this October. We have now more than 100 students already in this study program. We start this winter term the second master, namely on human and artificial intelligence. You see also that this interdisciplinarity plays a major role also in our study programs, and we intend to start with the next one in the next year. And in 27, we will come up with our first bachelor, will be in computer science. And our goal will be, at the final end, we tend to be around 6,000 students with 200 professors. Our intermediate goal is to come up with more than 1,000 students in 2030. And I think we will manage to reach this. At the moment, we have two departments, and here you see a small overview. One is headed by Wolfram on computer science and artificial intelligence. We are 8 professors at the moment in this field. And the second is on liberal arts and social sciences, which is headed by Guiburg Uhlmann. And you see here the names of the labs or research groups that we have so far. You see already here, it's very interdisciplinary, also within these labs. And to give you a small overview here, who are here today, the green ones are here today. So Wolfram is here, Yuki is here, and Josef is here. I think they will also give some presentations here. And if you look at the denomination of these research groups, you will see they all play a role directly or indirectly when it comes to embodied AI. And all the new developments that come up with large language models and so forth. So we really set up for the future developments and challenges that come up in our society and in AI in particular. And the other department, you see also that it's called liberal arts and social sciences. Math is included here for the moment because we are so small. It's beside myself also other aspects that play a role in embodied AI, like discrete optimization, applied discrete optimization, and also things that we are dealing with is mathematical optimization in general, decision optimization, and things like that, with all aspects in playing a role in various domains, like in health, logistics, supply chain management, banking, and so forth. So this is just a short overview. What I should say, at the moment, we are very small. On the one hand, small can be a bottleneck. On the other hand, it can also be an opportunity for you to cooperate with us. You will have a direct impact on when you cooperate with us. There are a lot of opportunities, not only in buildings. We have an own campus with 60,000 square meters, which is open for industry, for our society, to address with us the challenges of tomorrow. So it's great for your interest. Thanks for your why, also from my side, to organize this, your interest in our university. And it will be great if you can come up with collaborations in this context. Thank you for the moment.
We are perfect in time, as you see, right? And as a German, I will keep track of this for the remainder of this workshop. Right? And Germans are always very strict when it comes to timing. We are going to start with the first presentation of this workshop, which will be given by Yuki Asano. Yuki, as you saw just on the previous slides, is a member of the UTN. You see all the wonderful color here again. He's a head of the Fundamental AI Lab and a full professor here in Nuremberg. Before that, he led the QVA lab at the University of Amsterdam. He also collaborated with Qualcomm AI. He got his PhD in visual geometry at the University of Oxford, where he worked with Andrea Vedaldi and Christian Ruprecht. And he also loves running, the mountains, and trails and their combinations.
Great, thanks. All right, yeah, thanks again for the organization. I'm really happy to be here. I'm very much looking forward to the conversations. Even though tonight I need to fly to Italy to a summer school, so I'll only be here today and until the afternoon, so let's have a chat and otherwise catch up via Zoom, etc. All right, so you can see my talk. Let's see whether this works. What's that? Oh, this one. Okay, got it. All right, thanks. So this is me. This has been said. These are my research topics. And I thought this picture is a bit old, so I used Gen AI. And so this is closer to how I look, I think. Let's see. This, very accurate. Although I don't like ties, so we'll see. Yeah, so a bit of a background about our lab. So Fundamental AI Lab, as my T-shirt also says. Also for short, Fun AI Lab, we tend to want to work on things which are like scientifically fun, so intriguing, and not just pushing numbers by a tiny bit. And so because of that, we're working on 4 main directions. Self-supervised representation learning, which is something we're going to be talking about today. Vision language learning, another one of the main topics also covered today. Then video and temporal learning and large language models. And I'm going to start with motivating a bit why I think videos are so essential. So first of all, I don't know how many of you have babies, but you shouldn't give this video to your babies, which is flickering images, which are non-consistent, non-coherent, even though this is exactly what we do when we train all the image models. All the image models in VLMs, like GPT-4o, all the vision models have been trained on these shuffled image sequences, essentially, right? This is not how humans learn. This is a bit strange. And actually, in humans, people have found, or in primates actually, that this sort of training data for real living beings is not ideal because it decreases your, actually, your quality of vision. And yeah, despite that, current foundation models are all trained with images. And I think videos allow us a new couple of directions, right? It allows us to train more similarly to, yeah, human cognitive development happens. It allows us to understand some sort of physics, like in this video. If I just gave you a single frame, you wouldn't know what's happening. And to be fair, you probably still don't know what's happening. It's some sort of cheese festival in the United Kingdom. But you get the point. You cannot understand physics without time dimension. And lastly, of course, for embodied AI, this is absolutely essential, right? You cannot really start making a soup if you're only understanding a single image and saying, oh, it's a kitchen. And yeah, so what? What comes next? And of course, nowadays, probably more than 80% of the internet traffic, I don't know, someone from Huawei probably knows better, but is video data, right? Like all the stuff that's being streamed, it's just an insane scale. And if there's something we know about deep learning is that with scale, everything becomes better. Besides that, so I mentioned the scale, the weakly supervised, so that's the clip sort of data, right? So that's image and captions. Like if someone posts on Instagram and says, this is a cute animal, this is a weakly supervised data set, but still, if you compare that to all the raw data that's being collected via, let's say, satellites, all kinds of microphones, cameras, it's tiny. Of course, self-supervised learning has the benefit that you don't need to relabel because you're not using labels, and things like cars constantly change. So if you're training your visual encoders based on these labels, you will have a problem, unless you have like very specific types of cars, which is very boring. And lastly, if you want to train vision models, you don't necessarily want to incorporate some biases in them. For example, if I type in house into Google, all of these are houses, but that doesn't mean we want our vision encoder to put all of these images into one vector that looks the same, right? They're clearly different in different contexts. And of course, for me, fundamental understanding, how far can just data go? When do we start needing labels, and how far can we just go with pure data? And so one of the works that I'll present first is called Is ImageNet Worth One Video? Learning Strong Image Encoders from One Long Unlabeled Video, and we presented this at iClear as an oral and outstanding paper last year. And the key question we wanted to tackle here is this question that I mentioned. How powerful is time in video-based pre-training? And so, yes, we could have collected a bunch of data sets or combined or analyzed some things, but we wanted to sort of study the extreme. Let's see how far can we get by taking a single video and training a neural network from scratch. So a single vision transformer, train it only on a single video, and how good can it get? And of course now, the choice of video becomes a bit important. So you can either pick a long video, or it should have semantically rich content, so lots of stuff. But then it should also be high resolution because you have more data. But that sounds like curation, right? And I just said I don't like curation, we want self-supervised learning. And so then the solution is actually to get out and have a walk. So literally, there's thousands of people doing this. They wear a GoPro here in the chest, and they just walk through cities and just collect footage. And this genre is called walking tours on YouTube. You can find thousands, tens of thousands on YouTube. And the videos look roughly like this. So you can see they're high resolution, semantically pretty rich. I mean, everything you see in cities, and also they have them in suburban environments as well. Moreover, they're continuous videos, so they're not like movies where you have constant scene cuts or like zoom-ins into particular faces. And also compared to things like ImageNet, where it's impossible for a single human to look at all the images, here you just sit down and watch a video for 2 hours, and you know everything that's in your training data. So we proposed this new data set. There's 10 videos of 4K quality, which have permissive licenses, so even commercial use is fine. And alongside this, we proposed a new method called DORA, Discover and Track. And I don't know who knows this. There's this cartoon called Dora the Explorer. And similar to that, we walk around and we learn from what we see. And the high-level idea is as follows. We track multiple objects across time. So that's sort of a tracking thing. So if we're walking through the streets, we're going to track a car, we're going to track a bicycle. And then we're going to enforce invariance of the features across time. So a bicycle at frame 1 should be still the same features as a bicycle at frame 5, let's say. So in detail, and I'm going to keep it very high level here, we have multiple frames here. We're going to turn them into patches, like in a vision transformer, push them through the vision transformer. Then we have this, what I call multi-object tracker, which we'll get to in a bit, which gives you object masks per frame. So it looks roughly like this. So in the first frame, the object is here. In the second frame, it's there, and so on. And then we're going to push them through the encoder again by masking out everything else and just apply a normal dyno loss. So this is a fairly well-established self-supervised loss that's based on clustering, which I'll explain more in the next paper, actually. And we do this, actually, but for multiple objects. So that's roughly the loss. Now this multi-object tracker is a sort of interesting part, because I just said we don't want any curation, and tracking is typically trained with a supervised data set where people have annotated things. So instead, what we want to do is we want this multi-object tracker to be self-supervised. So we don't want to enforce anything apart from, like, we don't want to use extra data. So what this tracker is, it's actually just inside the vision transformer itself. So we will recycle the heads in the vision transformer. So just like in LLMs, vision transformers have multiple heads, multi-headed self-attention. And typically, these heads tend to look at the same spots in an image. So if there's a cat in the image, all the heads will focus on the cat. However, if we want to do multi-object tracking, we want each head to be looking at different things. So one head looking at the cat, one head looking at the dog next to it, and one head looking at the background, let's say. So this is a problem if you just use the VIT normally. So what we do instead is we use Synchron-Knopf optimal transport for enforcing a high entropy alignment. So that basically means that each head is encouraged to look at different locations. Where to look, that we're not supervising. So we're just saying overall the assignment needs to be high entropy, but you figure out yourself basically where to look at. And now let's take 3 heads and let's visualize where they're looking at. So 3 heads, that's easy. We can just say head 1 is red, head blue is green, head 3 is blue. And so whenever you see a pure color, red, green, blue, it means one head is looking at it. So the car, only one attention head, the blue attention head is looking at. However, we also see these turquoise and yellow areas in the image. So that means 2 heads are looking at it. So turquoise is obviously the mixture of green and blue. So that means 2 heads are already looking at this. This is if you don't have the Synchron-Knopf, our novelty here. Instead, if we apply Synchron-Knopf, you can clearly see, okay, 1 head is looking at this part of the building, 1 head is looking at the car, and 1 head is looking at the scooter. Moreover, you can see that the tracking nicely works. So you can see the scooter is being tracked by the same head across frames. Same with the car and same with the background. So actually what we have is that this multi-object tracking ability just emerges out of the self-supervised objective in a VIT. And you can see this in these videos. They are slowed down, but you can see the person in blue is being tracked, the traffic light in green is being tracked, and so on. However, this wasn't really our goal, right? We wanted self-supervised representation learning from video data. So let's compare it against what was back then the state-of-the-art, Dino. So first of all, we see that we use the Dino learning method on a couple of data sets, on a movie data set or on our walking tour data set. And we can see that compared to the Dino learning method, actually applying our new Dora learning method works much better. So on every data set we tested, our learning method actually worked better than Dino. Moreover, walking tours and our learning method Dora, they are a great match. I mean, it makes sense. We sort of proposed it for this type of data. And in walking tours, there's a lot of stuff going on. So just Dino style, one thing happening per image is not sufficient. And if we compare it now on standard downstream benchmarks, such as semantic segmentation on AD20K, we can actually see that even Dora trained with one single walking tour, WT, video, performs better than Dino trained on ImageNet. And if we use 10 walking tours, which is the whole data set we have, which is approximately 1.5 million frames, so it's roughly the size of ImageNet actually, it performs much better. For other benchmarks, as soon as we get to the point where we use 10 walking tours, we are actually better than Dino almost everywhere. So roughly with one walking tour, we're on par with Dino. If we use 10 videos, we actually outperform Dino almost everywhere. So yeah, the key takeaways here is that training strong encoders from scratch, even with a single video, is possible. We can match the performance of Dino back then trained on ImageNet in terms of performance. The key idea was that we have this spatially dense loss, which is based on multiple object tracking. And lastly, this whole thing, and why I brought this presentation here, is that I think these walking tours are A, great for training vision models, and B, of course, you might have thought about it, it's very similar to how a robot would see the world if they're moving across the street, right? They're literally walking through somewhere and recording data. And you can imagine, like, if you had a whole fleet of robots, how many data points you could collect and how well this would scale in terms of performance. All right, so I would say, like, questions at the end, probably for ease of purpose. Next, I'm going to present Franca, our newest work called Franca, Nested Matryoshka Clustering for Scalable Visual Representation Learning. It's sort of a collaboration between France and Franconia, which is where Nuremberg is. That's why we called it Franca. And also Franca means, in Latin, the free one, because we have open source data, open source model, open source code. Yes, and our motivation here was that until a few weeks ago, Dino v2 was the best vision model you could have that's self-supervised and that works across all kinds of tasks. But Dino v2 has a few things which are hidden. For example, a big part is the training data. It's proprietary. So yeah, generally self-supervised foundation models are hard to obtain. There's only a few works from Apple, from Meta, again from Meta, and we had our Dora work, and now we have the Franca work, which is the new model we propose here. And now I'm going to explain you a bit of the predecessor, Dino v2, because that's essentially on which we build on top of. So Dino v2 and also v3 basically work in the following way. So you have an image, and you take augmentations, such as cropping. People typically differentiate between global crops, there were big crops and small crops, local crops. And then we apply masking as well, which is just another augmentation, and these get pushed through a student model and a teacher model. The teacher model is just the exponential moving average of the student, so they're directly connected. And then you get an output, which is the CLS token and the patch features. On the CLS token, you apply the typical Dino head, which is a clustering loss. And actually, this clustering loss is the one I developed in my PhD in 2020. And for the dense patches, we do the same. It's densely clustering, so it's kind of like self-supervised segmentation loss. And all of these are basically combined to yield the Dino loss, which is applied across the student and across the teacher model. All right, so this is the framework. There's not that much else to Dino. There's a few hacks in the training code, like weight decay schedule and things like that. But it also has a few problems. The synchron knob clustering is prone to numerical overflow. The clustering itself is happening in very high dimensional space. So it's clustering an image essentially into 130,000 clusters for Dino v2 or 262 clusters in Dino v3. That's a lot more than ImageNet, right? Like ImageNet has 1,000 classes, and even if you take all the possible classes, you probably wouldn't reach 262K. So that's a lot of clustering happening. It's very sensitive to hyperparameters, and the features have a high positional bias, which we will get to in a bit. And as I've mentioned, they use a proprietary data, and also they use data which is, so I call them CVPR data, because they use all the popular computer vision data sets and put them in the pre-training data, and then they test on these data sets, and of course this gives you gains. But the proprietary part is a difficult part, which means we cannot reproduce anything. So first of all, we have a new training method, which is called Matryoshka clustering. So it's fairly easy. So we have the encoder, just like in Dino, it's a vision transformer, and we scale up to vision transformer G, so very large models. And now we apply Matryoshka embeddings, which sounds complicated, but it's very easy. We just take the features which come out of the network, and then we're going to give an importance score to each neuron. So basically, we're going to say the most important content of the image should be in the first part of the neurons. And then we can gradually have mutually expanding sets of neurons that need to gradually capture more and more semantics. So we use the first, let's say, 256 dimensions, and that gets a clustering loss, and it gets a different head. And then we use the first 512 dimensions to have another clustering loss. So you can imagine that you can get gradually more fine-grained classification the more dimensions you have. And therefore, we also have the number of clusters scale with the division, with the number of neurons we're using. So coarse heads can capture very global semantics, like dog versus cat, basically, and the fine-grained heads can differentiate between Chihuahua and Labrador. And what we can see is that this sort of importance ordering works. So if we use only half of the dimensions, or even if we use just one, we take all the dimensions, so depending on the model, let's say 2,000, and we divide it by 128, you can still see this typical Dino-like part structure emerge when we visualize the image with PCA. All right, so that's one thing, and I'll get to quantitative results in a bit. But I mentioned this thing about positional biases. And I think we agree that we want the features from our vision encoders to encode semantics and not the position of a pixel, because the position of a pixel, you can get from layer 0. It's literally the position. So I think this is a reasonable statement that almost everyone agrees. But no one has actually analyzed if this is true in vision models. And so we have a preliminary analysis where we do the following. We just take an image, and in this case, the image has, for example, 4 patches for simplification. We get the features out of the model out, and the same for another image. And then we're going to cluster all the features. And we're going to track, for example, if cluster 1, what ended up in cluster 1. So from which image did it come from, and what kind of location in the image was it? So which row was it, and which column was it? And we can take a look at that. And yeah, we can also reformulate this in 1D instead of 2D. And then we can compute an entropy score per cluster. So what we want is that we don't have clusters which only encode position. So if the cluster has very low entropy, that means this cluster only has patches which are in the top left, and it doesn't matter which content. And so this is exactly not what we want. So low entropy bad, high entropy good. And in fact, in Dino, you find lots of clusters which are low entropy. For example, on the left-hand side, I visualized cluster 435 and 9,320, which all encode just the position. So no matter what the content is, it's always the same patch location, which is pretty useless to have that out of a vision encoder. The histogram on the other side, so I first want you to just focus on blue versus green. Blue is Dino v2, so overall average entropy 2.6, and green is our Franca model, which is on average entropy 4.8. So it's a lot more semantic. And this RASA, which I hint here, further increases the entropy by a bit. And this RASA is a new method which we also propose in this paper alongside this new clustered training objective. RASA is a post-pre-training method, so that means you can take any pre-trained backbone and apply it, and it just takes a single GPU, it takes a few hours. And you can apply this on top of a clip backbone, on top of Dino v2, on top of anything, essentially. And what does RASA do? So again, you push the image through the vision encoder, you get the features out, and what we will do is we will train a linear layer that predicts the position, right? So it does exactly the thing that we want to avoid, basically. And we have an MSE loss in terms of prediction loss, and we only train the linear layer while keeping the encoder frozen. Okay? So you might think, why do we want to do that? The reason is that a linear layer can actually be a linear layer that predicts x coordinate and y coordinate can be understood as a row predictor and column predictor. And together, these two linear predictors create a hyperplane that we can subtract from the embeddings. So what we will use is the Gram-Schmidt orthogonalization procedure to exactly subtract the component which has the information on the position. So it's a very simple, mathematically it's very simple, and it's a linear transformation. And so we train this linear predictor, and then we remove this component like this. So we have a linear layer that has removed the positional information once, and then we do it again, and we do it again. And we can do this iteratively, and all of these are just linear layers. So at the end, multiply linear layers together, it's still a linear layer. So in the end, you don't need to change the files of the VIT. You can all absorb it back into the model. And RASA successfully increases the entropy on all the models that we've tested. So even on Dino v3, it actually increases the entropy that we just talked about. And this, I don't have, I think maybe later I have the table here, but this gives you huge gains on dense understanding tasks. So everything from semantic segmentation to in-context learning for dense tasks, this RASA approach improves because the models are not biased by position anymore. All right, here's another overview of like Franca versus other existing open source models where they are either open weight or open data or open code, but none of the existing models is basically open everything, which in our case is a case. We use open source re-Lion data, so it's Lion data that was cleaned and thoroughly checked. We use 600 million images compared to Dino v2, which uses 142, but curated from 1 billion, roughly, and DynoV3, which uses 1.7 billion images. And so the typical way to visualize dense features is by running PCA on the individual features of the image. These images were actually randomly picked by, not us, but by Python, basically. So we're not cherry picking here. And you can see DynoV3 is a big upgrade from DynoV2, right? And DynoV2 with registers even works better. Radio is a supervised method which uses semantic segmentation, so of course it looks very good. But then if you compare our method, Franca, it actually is doing very well. So from the top, the airplane outline is very clear. The automobiles next to the airplane are very clearly distinguished compared to DynoV3, which sort of puts them very close to each other. And also the bicycles have a different feature compared to the riders, which makes sense. Well, for example, for DynoV2, they're all the same. In terms of performance, here we can actually compare on the same pre-training data. So this is all trained on ImageNet 21K, roughly 16 million images. And we can see that Franca beats all the methods that were trained on the same data. So this is the most fair comparison, because actually the data is the same. We also compare against some other large open data self-supervised learning methods. So there's WebSSL, which uses 2 billion images, but it's fairly open. It's kind of reproducible, while we use just 600 million. And yeah, this is the gain that we get. And on out-of-distribution tasks, we're also pretty much on all the architectures better than DynoV2. And sometimes we're even better than DynoV3, for example, for unsupervised object segmentation or discovery. All right, so in the last few minutes, I want to talk about this other part of my talk. So we had learning from moving and now generalizing from LLMs. And here I'm going to be talking about a paper called Visual Alignment in Text-Only LLMs, New Frontiers in Data Efficiency, from Jona, Gertjan, Sergi, and myself. And the motivation here was the CLIP paper, and actually a reproduction of the CLIP paper from Meta AI, where they analyzed the statement that CLIP generalizes because they use language. That's why CLIP works so well. But is this actually the case? And this paper really gives you a lot of insights. They have a huge appendix, and in the appendix you find this table, page 14, measuring task alignment. So the top row, and I know you cannot see the details, top row just says performance, and the bottom row says how many of these classes were in the pre-training data of this meta clip. And then they have the statement, interestingly, there seems to be a correlation with the accuracy and the number of classes matched in the metadata. So what they're saying is, if CLIP performs well on a data set, it means that data set was kind of in the pre-training data. If CLIP performs not well on a data set, it's because that data wasn't in the pre-training data. So CLIP, sort of the conclusion is, for the most part, is evaluated within domain. It's just a very big domain. They didn't really measure any sort of generalization. But we think, and I think intuition tells us, that language should help us do the generalization, because language is very abstract. It knows that a rhinoceros has a horn and a unicorn has a horn, for example, right? So there's something about language that should help us generalize. And so we wanted to investigate this, and we proposed a new method called shared vision language tuning, or ShareLog for short. So compared to CLIP, which trains both vision encoder and text encoder from scratch, or LIT, which keeps the image encoder frozen and trains only the text encoder, we keep both of these encoders frozen. And we just train a single MLP which maps one modality to the other modality. What this means is, A, we're very efficient, so we can fit a batch size of 16,000 on a single GPU, while CLIP needed 200 GPUs to do that. And moreover, instead of using typical BERT-style encoders, we actually use decoder, LLMs. And that's one part. We propose this because by not adapting anything, we're actually checking, is this information already inside the LLM's representation, right? If you fine-tune everything, it's all because of the data. But we want to know, does the LLM know which objects have what properties? And so in addition to that, we also need a clean evaluation. And for this, we propose mutually exclusive dataset splits. And it sounds fancy, but it's very simple. You can imagine as taking ImageNet, taking the first 500 categories and making fake captions that say a photo of A and then class name. And then you train your vision language model with that, and you test it on the other 500 categories. And this will now tell you real zero-shot class evaluation, because previously you had a language model and a vision model, and the only paired data was the first 500 categories. So if it performs well on the last 500 categories, you can measure the real generalization ability that comes from LLMs. All right, and for the LLMs, we actually use last token pooling, which has been shown to work pretty well, and we just apply our MLP here. All right, so what did we find? First of all, what we found is that previously people used encoders, but actually, if you look at it, these new billion-scale LLMs give you much better generalization performance. And these are the performance numbers, accuracy numbers on the zero-shot generalization. So these models can really generalize well on unseen categories. And actually, the best stuff you get is from decoder-style LLMs. And now, with decoder-style LLMs, we can measure how well they work. So this is now on the x-axis. MMLU, Massive Multitask Language Understanding Task, is typically used for evaluating how good a language model is. This we plot on the x-axis. And on the y-axis, we have the score that I just talked about. So how well does the model generalize when you use it in a Sherlock vision language model? And what you can see is that the performance actually correlates with the text-only performance. So, and this is a key thing. That means that better language models have a better representation of the visual world. And that's great news for computer vision, because we just need better LLMs, and we can actually generate better vision language models for free, which is really amazing. So the fact that this correlates, it's not a clear scaling law, but it's a clear correlation. Yes. And then, of course, we can use the framework also to train on larger data sets. So, for example, 12 million image text pairs. We can train our Sherlock framework. That's in the bottom part here. That's the largest data set we tried. And we beat all the other models that have the same training data just because we use very efficiently the pre-trained components. And because we use a frozen LLM, actually we score much better in using other languages. So we still only train with English text pairs, but our model does a much better job at, for example, understanding Chinese captions or Italian captions compared to the normal CLIP model. Yeah, and it scales pretty well. And the summary is that it's a very lightweight framework, so 16 GPU hours, 16,000 batch size for 20 hours on a single GPU, and you can get a CLIP-like train model. We get high zero-shot performance, and we actually showed that better LLMs have better visual representations. And then in the last minute, the question is sort of, where do we go from here, right? I presented these works, learning from videos, getting to state-of-the-art vision encoders using open data, open source, and generalizing from language. And I think I want to go back to the title, which is Vision from Moving, that robots collect videos, sensor and action data. I call this from robots for robots, and we can pre-train these foundation models on millions of billions of hours. And then we have this generalization from language part, which is a bit more high level. We can get world and procedural knowledge from LLMs. They know how to generalize. We can summarize and infer semantics and generate goals and what to do next. And similarly, in instructions, reward signals, we can apply RL pretty nicely nowadays in LLM space and guide how the system keeps evolving over time. And so we can keep going in the cycle. And yeah, I think this is a great fit for a potential large-scale topic between UTN and Huawei. And in German fashion, I think I'm ready for the questions. Thanks.
Are there any questions?
So one question for your vision. Robots collect videos, sensors, and action data. How do you make these robots collect? Is real robots?
Yeah.
Can you explain a bit more to the first point? Robots collect video, sensor, and action data. How do you reimagine? So from robots for robots?
Yeah, so I think there's multiple ways, right? I mean, in a way, Tesla is already doing this, right? Like they're driving around, they're collecting exactly the data that they will need afterwards. And I think any sort of walking robot will be able to collect these data really quickly, right? I showed that you get dyno level or ImageNet level performance just with a single 2-hour video. So if you have 10 robots walking for 10 days, you already have much, much more data. And of course, like the diversity depends on where the robots are walking, but that's sort of what I was thinking, yeah.
Okay, but I see potentially the challenge is that, I mean, you have millions of Teslas already running on the street. That's why you can collect Tesla data for Teslas or for other automatic vehicles, but now we don't have millions of robots walking anywhere, and how to solve the chicken and egg problem then?
Yeah. No, I think that's exactly the interesting part. I mean, I think, of course, initially the robots, if we imagine the robots will be walking around in fairly controlled environments, and then because of this loop, I think they will start becoming better, and they will start exploring more and more, and I think there's this positive spiral that can happen. Yeah.
Yeah, thank you.
Thanks.
So because we're broadcasting everything, please, before you start, wait for the microphone. Right.
Okay. Thanks, and very nice talk. I really enjoyed it. But probably I have one technical question about removing the position information from the image. So here you claim that you used a linear layer to remove the position, but actually you used three layers. And you said that you're combining 3 layers. Actually, you also did one linear layer. But I'm curious, why do you use the 3 linear layers, and what does it represent for each layer?
Yeah, no, that's a great question. In theory, one linear layer should do the job, but all the positional information inside of dyno or clip embeddings, it's very entangled. So it's not easy to extract all the linear information. For example, a very simple example would be if you suppose the positional information is in 10 neurons, then training the first linear layer just needs the first 2 neurons to get perfect accuracy. And then we remove this part. And then you still have 8 neurons left which have the same information. And so that's why it's an iterative procedure. And we do it 9 times. And we just do it on Pascal VOC, so it takes 10 hours or like less. So this is a very quick thing, yeah.
Thanks.
Interesting.
Yeah.
Hi, Professor. I'm coming from Huawei optical product line. We are researching at home robots right now. So my question is, we want to make the home robot to be becoming more and more smart without very few data. And we don't want our robot to be taking too much times for the installation. So I think it's a great idea. You mentioned that self-supervised learning. So my question is it possible to have some simple cases to make the robot to run first in the home, and we collect some few data for some online trainings to make the robot becoming more and more smart.
Mm-hmm. Yeah, I mean, I think one thing that's definitely the case is that these models get better once you get more data from the domain. So I would say like a good starting point is having a generally good pre-trained model, and then get the data from the domain, incorporate it in the pre-training mix, and, for example, do some sort of post-training, which we also have some works. I didn't show it today. But, yeah, and then you get better performance in the domain, for example. That would be a good starting point, I think. Yeah.
Okay, thank you.
Thanks.
Yeah, thanks a lot for the very impressive talk. So my question, I have first question about the tracking approach. Where you mentioned that you just position like having a kind of a normal camera you walk around, but does it make also a lot more sense, or do you think it's also helpful that the camera also zooms and also kind of actively changes, for instance, exposure, zoom level, maybe even rotate a bit so that we are exposed to different, variations of the property, so that your tracking actually see different characteristic of the same object, learn this in variation. That may be helpful for the generalization, right? Or what is your opinion?
Yeah, no, I think that's a great question and also like a great research idea. I think like if you know, for example, if you're a robot, you know you just walked around the chair, then you still know it's the same object, it's just a different side of the same object. If you had this information, this would help you a lot, I think. Right now, these videos are passive, so we just observe them, and sometimes the person turns left, sometimes right, sometimes stands still, or looks up or down, but we don't have the information what they did. If you had that, I think you could get a much better understanding of the physical world. You would know that a laptop is like has this surface on the top side, but if you turn it, it's very thin, for example, right? And if you knew how you were moving, you would learn that much more efficiently, I think. Yeah.
Thanks. My second question is that, for instance, like if you look at this two work you have done there, I mean, the first one is about video, learning from video, another one from much richer set of static images, right? So is there any chance you see how to combine them to push, let's say, the performance of the pre-trained model to a next scale, or is there any benefit, let's say, putting these two together?
Yeah. No, I think that there's a big benefit. So we have two works at ICCV, both at ICCV actually, where we take a pre-trained image model, in this case Dino or Dino V2, and we post-train it with videos. So first images, then videos, and this works really well actually. So I think that's one potential direction that makes a lot of sense for me, because a lot of basic understanding like edges, patterns, you can learn from images. That's fine, you don't need videos. But then the stuff which comes afterwards, an apple falls down or like you turn up object, I think that needs to come from videos. So I think this ordering is fine. Or if you have enough data, just use videos all the time. Because videos contain still images as well. So
we can use videos as a kind of in-domain data to kind of post-training before we use maybe the final label data to train.
Yeah. So we used videos as a post-training to get better dense features. So again, better semantic segmentation and spatial understanding. Yes.
Okay. Maybe I ask my last question reverse. so interesting. So about generalization, because field of computer vision, people are talking about generalization. For a few decades already, but the game has changed so much since now we have. Before the generalization, of course, we trained our domain that we try to have a clear separation. Yeah. Okay, now is out of domain, right? Generalization. But since now we have the pre-training data, which is so large, it's almost exposed to all kind of data that human has ever collected, the internet level of data. So having this clear separation, what would be our test data, is not going to be possible in some sense, because we don't know, for instance, a Dino, what exact data that it has been pre-trained, right? So in that sense, do you think that in the future, how we define the term of generalization should be also changed? This game, somehow also including evaluation, should this be kind of also adjusted to reflect what we are having now?
Yeah. I think we need to be a lot more careful these days, and that's why, in a way, that's the reason why we wrote that paper, because people talk about clip doing zero shot, but it isn't really zero shot. It's maybe few shot, just because the data was that big. But I still think generalization is important, even if you have huge data, because there will always be some random combination which you don't know, and that's where you want the model to perform. And if you just say, we train on the world and we evaluate on the world, which I hear very often, then I think you get problems like these small LLMs where you say what should I eat for dinner? And then it will start saying, you should eat for dinner 8 times 4 apples, and that's 12. Oh no, wait, and it's overfit to MMLU or GSM-8K. And so that's what I think, if we don't care about generalization anymore, then we will only get overfit models, and that's not good. I think we should still have data sets which really weren't in the training data and which actually need some sort of transfer. Yeah.
Thank you very much.
Thanks.
Final question.
Okay, thank you. Thank you, Professor. I'm wondering if it's enough to only use the video data to train a general purpose robot, And if it is, how much roughly videos do we need to do that?
I mean, I think there's, for training a model that actually runs on robots, there's some other experts here. For getting good vision encoders, I just showed you like very few data is actually enough if the data is high quality. But of course, we know the more data, the better. But the same goes for like LLM space, right? Like you can train on the pile or you can train on refined web, and you have radically different curves. So better data is always better.
Okay, so do you think that synthetic data, for example, the video generated by Sora or Jamie 3 like that, is possible to be used for training of this kind of?
Yeah, that's a great open-ended question. I think personally not yet, because even at the moment you can use images and they're okay. Like you can train models from scratch, but if you make like a fake cityscapes or fake ADE, it's never as good as the real data. So we're not quite there yet with images, so we're not there yet with videos for sure. But in the future, I think it will be very interesting, yeah.
Okay, thank you.
Thanks.
One question that just popped up. I mean, this is really great work, and I'm wondering, like, if you think about embodiment, right? So we are acting in the real world. Do you actually envision that if we once get into the situation that we can actually have systems acting in the world, not only changing the camera zoom or like rotating images, but actually manipulating the world, that this will get even better?
Yeah, I mean, I think that's really like the thing which really then will get close to like perfect imitation of how humans learn, right? And I think this has the most promise, because then the model can actually see the consequences. It can learn about affordances, physics. It can actually do experiments. I mean, just like cats sometimes push this, like, or babies, and it can actually learn about things. And this would be like, I think, the real where we want to get to. Yeah, everything in one system with like goal setting, exploration, self-supervised learning. Yeah.
Thanks a lot.
Thanks.
This brings us to the second talk of this morning. It's going to be by Jan Pfister. And so if you're, it's over there already? Okay. Yeah, great. So we are going to spread the scientific landscape, or jump over the scientific landscape now from computer vision to language. And like, you get a presentation about large language models. So Jan is a doctoral researcher at the University of Würzburg. His supervisor is Andreas Roto, who has a chair for data science in Würzburg. He works in the field of natural language processing and is interested in developing novel methods for understanding and extracting meaning from text. He works on using large language models, also in combination with pointer networks, to capture the complexities of human language. For my students who were wondering what was happening during the Christmas time, after we got this giant computer in Erlangen, it's 400 GPUs, a brand new system, and all of a sudden this entire computer was used for several weeks. Nobody was able to run a single job. You will now see the outcome of this.
Sorry.
Jan, no, say it's pretty cool. Go ahead. Jan.
Okay. Hi, I'm Jan. I'm from the KAIDAS at the University of Würzburg, and today I'm going to talk about how we pre-trained our language models entirely from scratch in German, not only how we did it, but also why we did it. It's the wrong one, I guess? No? Oh, no? Oh, it's this one. Okay. Okay, first of all, the KAIDAS is the Center for Artificial Intelligence in Würzburg. It's a rather large research conglomerate of up to 30 professorships, and it's also part of the Bavarian AI network. The idea is to bring, I would say, core AI and machine learning chairs together with application-driven chairs. So we have core AI chairs, for example, Goran Glavaš for natural language processing, but then also like application-driven chairs like Dominik Grün for quantitative single-cell biology. And these try to bring the AI and machine learning advances into their respective application fields. Now, I'm at the data science chair at the KAIDAS, and we are roughly, I would say, partitioned into 4 areas, all centered around deep learning. We do environmental data science like climate modeling, then also AI security and fraud detection, which then also contains anomaly detection or explainable AI. And finally, there are recommender systems like your average product recommender you think of. And the work where the part where I'm working in is text analysis part and natural language processing. Here we oftentimes cooperate with digital humanities, and this is also where most of our research is motivated by. For example, we oftentimes work on rather large amount of novels. Novels are long content texts, which oftentimes do not fit into our standard BERT or Roberta models that we use because they only have a very much shorter context window than these novels are long. So we also revolve around several different smaller and auxiliary tasks, I would say. For example, segmentation into scenes, where we try to break down the novels first into more handleable, shorter sequences, sub-chunks, for example, scenes where either the characters change or the time changes. And if you have broken down your novel into these sub-chunks, then you can more easily process them further for other downstream tasks. Like, for example, sentiment analysis. Here on the right, for example, is a small graph of sentiment. I believe it's either Harry Potter, I guess, or a Lord of the Rings, where you can see that the sentiment changes as the story progresses, and shortly before the end, the sentiment dips. Yeah, it's getting dangerous, and then in the end, the sentiment is rising again, which means, okay, thank you, which means that there is a happy end and everybody's happy. Okay, now how do we do this usually? For example, in LitBERT project, we work on extracting knowledge that is present within the language model, but also present within the novel, into a explicitly structured knowledge graph. Meaning we take the knowledge that is present in a novel, we try to use language models, and then try to structure all the knowledge into this knowledge graph, which then explicitly models how characters within the novel, for example, interact with each other, what the relationship is, where they are, and so on. And then we can also use this knowledge, this explicit knowledge, again, to feature it back into the model and make it accessible to the model. This we usually do with BERT models, of course, where we either do the task of knowledge graph completion, where we ask the model, here's a partly filled knowledge graph, which links are missing and or which nodes are missing and how are these new nodes connected to the already existing knowledge graph. Then we can, for example, train the language model on this explicitly made knowledge and either pre-train it further on this knowledge or even make it embeddable and then make it accessible to the model in this way just directly. Okay, motivated by this, our endeavor into pre-training language models started in about 2023, which is also roughly where this figure is from. Honestly, we looked at this figure. There on the left in red are the encoder models, on the right in blue are the decoder models, and we looked at this and we found actually there's very little German here. All these models are either pre-trained entirely in English, or they are pre-trained multilingually with German as an afterthought, I would say. There is a little bit of German sprinkled in, but it's not really a core idea to make a German language model by anybody. This can also be seen if we take a look at the pre-training data mixes, for example, from Llama 3, which was pre-trained on only 8% non-English data, meaning the German data within this language model is even much less. And even the natively German undertakings, I would say like Teuken 7 billion parameter model, has only 9% of German data, which is 320 billion tokens. And for most of the closed source models that are in use today, this knowledge is actually no longer given at all. So you don't have any idea how much German is in these models during pre-training. You can also make it more transparent or more visible by this, I would say, rather whimsical example, where we try to come up with a question that was definitely not present in the pre-training data. So we tried to come up with a question to really bring the model out of its in-distribution during pre-training. And we asked it this question: what does David Hasselhoff have in common with Markus Söder, a politician? And the model gave this answer. You don't have to read it, it's hallucinated, but this is actually okay. The much bigger problem for us was in bold here highlighted are all the grammatical issues that are present in this answer. So for example, in the very last sentence, the model generates a sentence that doesn't make any grammatical sense, and the names that it comes up to two bold markings before actually are not German names and more sound like literal translations from a name in a different language, but we're actually not even sure where they come from. So despite this being a state-of-the-art frontier language model, open language model, at the time, it was actually not able to generate, I would say, 2 sentences of proper German, right? So what we asked ourselves is, how did these models actually even learn German? Where did they learn German? So on which data were they tuned for German? What do they know about German culture, and from where? Do they know it from primary German sources, or is it just cross-transferred from, for example, English or other multilingual data? And where are shortcomings in German for all of these models that do exist? In order to change this, we set out to pre-train our own language models, which was actually part of a master thesis I supervised by Julia. And we basically played the entire pipeline of language model pre-training. First of all, to pre-train a language model, of course, you need the data. For this, we took the Red Pyjama dataset, which is a common crawl subset, which was published about 2 years ago. And if you download only the German part, you get about 30 terabytes on disk, which amounts to roughly 2 trillion tokens in German. This has then already been, I would say, quality filtered by the Red Pyjama team. But, for example, this sample still stays in. And this is neither German, nor is it high-quality natural language, I would say. And this can be explained because Red Pyjama did pre-filtering based on a smaller language model that they pre-trained on Wikipedia, and then tried to use the perplexity of the language model to filter out other Wikipedia-like text, meaning text which scores a low perplexity, stays in. The issue now is that these guitar chords actually score a low perplexity just because they are highly regular, meaning even the small language model is able to predict what comes next, despite this not being natural language at all. So we did our own filtering. We actually applied 2 separate filtering steps. First, we took a German tokenizer and measured into how many subtokens a word gets divided. And if this ratio becomes too high, a German tokenizer cannot adequately represent this word, and then we kick it from the pre-training, assuming that it is not native German. And also we did some hash-based paragraph deduplication, as document-wise the data was already deduplicated, but we found that, for example, GDPR notices like DSGVO disclaimers were very much present over the internet and always embedded in slightly distinct contexts, but the disclaimer themselves were present all over. Okay, after this, we had about 1.3 trillion German trillion tokens available that we could actually train on. They stem from about 8.3 million unique internet domains, and the most part actually is from Wikipedia and I would say German mainstream media. There is of course a long tail, but this is the largest part. We did not explicitly curate any kind of coding data into the pre-training mix or math or reasoning data or whatever might happening at current state-of-the-art models, but instead we focused on this basic German knowledge basically. Now, how did we train our models? As first, as I said, this was a master's thesis, so we tried to train a 1 billion parameter model because we thought this was a nice sweet spot where some early scaling laws are happening, but it's still rather manageable in training. For this, we took the code which was used to pre-train the Tiny Llama 1 billion parameter model and adapted it to our needs. Because we wanted to make the model entirely transparent and entirely from scratch, we implemented, for example, data point tracking such that we could know when which data point entered the model during pre-training. And also we wanted to play around with various different scaling and sharding strategies, and for this we had to make some adaptations. Now, finally, we then published the model, and we basically also trained it with a full focus on transparency, meaning we wanted to address all the points that we raised earlier. We wanted to track exactly when which data point entered the model. We wanted to publish all intermediate checkpoints, and also then in combination, of course, you can analyze 2 different checkpoints from your models, and you also know which data points the model saw during pre-training in between those 2 checkpoints, Meaning, if you analyze them, you can actually take an understanding or try to estimate what might have happened during pre-training that made the model change behavior, for example. We also publish all intermediate evaluations of these checkpoints, and of course, all code and data. Okay, now finally, we found that it might be beneficial before training our 1 billion parameter model, which we had no experience in beforehand. It might be good to train a smaller model beforehand, like 120 million as a debug run, I would say. Later on, we also followed up with a 7 billion parameter model, and also finally a 32 billion model, which is not yet released. We trained them entirely from scratch, and this took us in Würzburg on our small cluster that we have, on 32 L40 GPUs for the very smallest model that we have, about 10 days, so over a week. Later on, we had access to some more GPUs where we actually retrained the same model, where we found that on 64 H100 GPUs, this took less than a day, so only 20 hours for the very same model. But here, this was done in Erlangen, to whom we are very grateful because they really helped us in getting this project started. They had very much better interconnect between the GPUs and much better networking, much better hardware, so this training naturally was very much faster. Our 1 billion parameter model was trained on 64 H100 GPUs for a month, and the 7 billion parameter model actually on 128 H100 GPUs, which would have cost us, if we had rented these GPUs at market price, it would have cost €250,000. So this is the run that ran over Christmas, so this was basically a Christmas present at our chair. And later on, we also trained the 32 billion parameter model on 304 H200s for 2 months. You always hear these, I would say, stories about GPUs failing, nodes failing, jobs failing, hardware issues, whatever. Actually, in all of these runs, we did not encounter a single issue of this kind. And also no lost spikes. We did not have to re-roll training, and all the horror stories you hear, we were completely blessed and did not have to do any of this. And the 32 billion parameter model was actually even trained on the beta axis, I would say, where the admins were like, okay, we just set it up 3 days ago, it's going to break, but go for it, and it just ran smoothly for 2 months. Okay, now how did we train on over 300 GPUs, you might ask, or at least we asked ourselves when we got this project started. And the answer to this is fully sharded data parallel. FSDP is natively baked within PyTorch and helps you to distribute your model across various different GPUs and nodes and use all of them together. In this very simple example, imagine you have 2 nodes, each with 4 GPUs, and then you have to consider that you might have some inner node connections, so between GPUs of the same node. You have to be aware of how fast your inner node connection is, and then also how fast your connection between your different nodes is, meaning your inter-node connection. If all of your connections were really slow, then you have basically no way around of copying your entire model weights to every single GPU and having your entire weights available on every single GPU, because every time you need something from a different GPU, it takes a lot of time because your connections are slow, and you cannot really scale this training. If you had a nicer setup where you say you have very nice interconnects between all available GPUs, then you can get away with distributing your model weights across all available GPUs, meaning every single GPU only holds a small part of the model, and on demand, this then gets sent around over the very fast network. There are, of course, some kind of hybrid strategies where, for example, only your inner node connections are fast. Then you, for example, can shard the model in a way such that on every single node, the model is available in full, in theory, across your various different GPUs in the node. Okay, how does this work? Just a rough overview. Here is your, for example, if you imagine this is a feed-forward layer, and your gray bar is one of the layers, then at rest, the parameters are sharded, meaning every single GPU holds a small part of this layer only. Then, when it is time to feed forward this layer, doing backward passes, it works exactly the same. The layer gets manifested and assembled in every single GPU. And this is done in basically some Hadoop-style all gather operations where every single GPU sends around its single part that it holds to all other available GPUs such that this single layer then gets manifested at every single GPU. And now you can see why this takes quite a bit of communication overhead. After the model is forwarded, you store the activations, so the output of your layer, and throw away the weights again for all GPUs for which this is not the assigned GPU, basically. Which means at rest, the parameters are sharded and distributed across your cluster, and only when this layer is used, then it gets manifested into your GPU memory as a whole. Okay, how well does this then scale? As a reminder, this code was used to pre-train a 1 billion parameter model on 2 A100 DGX stations, meaning on 16 GPUs across only 2 nodes. And we actually had access to the Jülich scaling days for 1 day, where they reserved a cluster for users such that they can show how well their code scales. And we were honestly a bit surprised to see that it scales up to 2,048 GPUs nearly linearly, after which it then begins to break down. So 850 node training actually is even slower than pre-training on only 850 nodes. And we were quite intrigued by this and tried to figure out what is going on here. And naturally, of course, we at first looked at the GPU utilization. This is I would say, actually rather simple figure. On the x-axis, there is the training run, meaning the time as training progresses. And every single dash of these pink ones in the beginning is a single node with 4 GPUs each. And a darker color or a reddish color means that the GPU utilization is low, and a bluish color means the GPU utilization is high. In the beginning, of course, the utilization is rather low because there's no work yet done. I don't know, InfiniBand is setting up, your code is loading, your data is loading, and so on, so the GPUs are doing nothing. And then as training progresses, your GPU utilization rises. And actually in both runs, the fast one on 512 nodes, the upper one, and the slow run on 850 nodes, actually both showed nearly 100% GPU utilization. And we, at first, honestly, were a bit perplexed why our model was training slower than if both of the GPUs were doing their best and were fully loaded, basically. We then found that it's also important to look at the power draw of the nodes. And we found that for the upper one, the fast run, the GPUs were drawing near the max of what they were able to draw within the node. And for the slower run on 850 nodes, it was actually closer to a half, I would say. And this, in hindsight, kind of makes sense because your GPUs are still being utilized at full. They are doing something all the time, just not what you're intending them to do. They are not doing your matrix multiplication, your feed forwards, your backward passes. But instead, they are doing communication overhead, right? They are just lost in sending model weights around and not doing any of the computations you wanted them to do. OK. Was it all worth it, you might ask? This was the original question that we posed to the Llama 8 billion parameter model. And our Lemline 1 billion parameter model then answered this to the very same question, which is still hallucinated, in our absolutely unbiased opinion, of course, a little bit less hallucinated. But most importantly, it does not make any grammatical errors, despite being 8 times smaller. OK. Basically, inspired by this success, we then consequently also decided to train encoder models from scratch, then in combination with the Digital Humanities Chair in Würzburg. And this we coined the modern G-BERT model because it is based on the modern BERT architecture. And we pre-trained 2 sizes, 134 million for smaller applications, and then also a 1 billion parameter model. And they are pre-trained on the very same data set as the Lemline model for comparison. These were trained on 16 8100 GPUs for 19 days. So training encoder models actually is much faster than training decoder models. Something that we heard of, but we were not aware that it is at this scale different. We also did some context extension up to 8,000 tokens because this is rather important in our research for handling long context texts. And we did this, of course, by finishing the training using some long context, high quality samples that were specifically picked for this. We also, as a comparison, tuned our Lemline models, our decoder models, into encoder models using LLM2Vec, basically to compare whether it is even worth it to train encoder models entirely from scratch, or if you could just use a capable decoder model, tune it into an encoder by some post-tuning, I would say, and just use that instead. This can be seen here on the right in a figure. The blue triangles is the original lemline models. On the x-axis, the further right, the larger the model. The higher the score is, the higher on the y-axis. And you can see that this blue arrow denotes the difference between original pre-training and LLM to VEC. So LLM to VEC transformation into encoder improved performance on embedding sensitive tasks. But the red dots being modern GBERT showed that despite modern GBERT being trained for much shorter time, just dominates all other models in this benchmark. There is just nothing close to this model currently in the German landscape. We also figured out we had to evaluate this in some way. And when we came up with this, we noticed there actually is no benchmark for this in German. There is no real German natural language understanding benchmarks. So naturally, we also set out to change this. And we published Supergleber, which is a natural language understanding benchmark for German, inspired by the English GLUE and SuperGLUE benchmarks. This contains 29 natively German annotated tasks, and we made sure that there are no automatically translated samples in the test set, for example, and that anything is dedicatedly annotated in German. This contains classification tasks, sequence tagging tasks like token classification, question answering, and sentence embedding. We build it in a way such that you can plug in any Hugging Face model you want. It pre-trains it on the data, or it fine-tunes it on the data, it evaluates on test set, and then you get out a ranking. At the time that we created this benchmark, this was actually done before we trained our models. The numbers are not that important here, but the benchmark was dominated by smaller German encoder models that were quite old at the time. Then we added our own models, of course, and we found that our modern GBERT again basically dominated all the benchmarks, even beating out some 7 billion parameter models, our own 7 billion parameter models that we pre-trained on our own. And for sequence tagging, like token classification here on the right, this is even more extreme, as the modern GBERT 134 million parameter model even beats out Llama 8 billion parameter model on these tasks. This is just due to the inherent structure of how the model encodes the texts in comparison to decoder models. Okay, now finally, of course, we also trained our decoder models, so we evaluated on some auto-translated, sadly, LM harness tasks for German. This is like Who Wants to Be a Millionaire style tasks, meaning you get a question and A, B, C, D, which of the answers is correct. And to be quite frank, our models are really, truly bad at this. These are already our instruct-tuned models in comparison to other language models that there are for German. And in our opinion, this mainly lies in our chat tuning, or this performance is lost in our chat tuning. This is our core shortcoming that we're currently working on. There are very few German chat or instruct tuning data sets such that you can train your models that you're able to talk to them, and they are either really small, of low quality, or just really not diverse, meaning you don't get a large general purpose chatbot out of this. We also experimented a bit with full fine-tuning, for example, for this chat tuning or QLoRa, and we found that while a nicely calibrated full fine-tuning run gives you a better chat model, it is also very much easier to break this model during training. Meaning if you do, for example, full fine-tuning with badly configured hyperparameters, your model will answer all of your questions, but it will just plainly hallucinate all the answers, even basic ones. Because likely it is, for example, if you have a too high learning rate, it is just not able to access the underlying knowledge that is present within the base model. If you have a nicely configured QLoRa run, you actually get a better results for this than with full fine-tuning. Now, you might say, why don't you just translate English samples into German and then train your language model on this? While, yes, this might help a bit, actually there are two problems with this. First of all, the English instruct tuning datasets that are publicly available are also not ChatGPT-like, meaning you don't get, if you train an English model on this, you don't even in English, you get a ChatGPT out of this, right? So there is this inherent gap still for English. And then if you translate this automatically to German, you have the issue that what I've shown you earlier about out-of-distribution samples. If you ask, for example, Llama 8 billion parameter to translate this sample into German, I showed you what kind of German you get, right, with grammatical issues sprinkled all over your text. So you do not want to train your instruct model on this kind of auto-generated content. So what is next for us? From an academic point of view, we would like to play around with the pre-training data set, meaning we would like to, for example, leave out some kind of domains or type of text, see how the model behaves, or also try to pronounce some domains more, like legal texts, medical domains, and so on. Then we would like to get some better instruct data sets. For this, also bilingual training could be a thing where we could leverage the English data sets, but then also instruct tune in German. This is also the reason why we pre-trained our 32 billion parameter model hybrid, meaning bilingual in German and in English in parallel, 50-50. And you would also need, for example, pairwise data to do all of your reinforcement learning tricks like DPO, this answer is better than this answer, and get rankings out of this. And to be honest, likely this is just a manual effort, and we don't see a way around this. Then also what we are working on is modularization, meaning we try to basically use adapters to also add, for example, other languages, going the other way around, not using a native English backbone as everybody else does, but instead using a native German backbone, being able to modularize in, for example, other languages or even modalities, like, for example, vision, speech, or even movement. Then, of course, as it is trendy, of course, we would like to play around with reasoning, trained entirely from scratch in German. But here I'm not even going to begin listing the shortcomings that exist. There is no data, no benchmarks, no nothing. So overall, we trained 2 German language model families entirely from scratch, entirely in German, all of them publicly available. You can just download them, use them for research. We also created a German language understanding benchmark. All of this honestly took about 1.5 years of work and effort, and was not really covered by any project, so it was more of a side project at our chair, to be honest. We got 2 papers out of this and a preprint. We learned a lot, whether we wanted or not, about distributed training, various different issues that can occur. And next up, we would like to do some instruct tuning and even implement this multimodality and modularity. Thank you.
Who has a question? Yuki.
Thank you. Thanks for the fascinating talk and the huge scaling. That's really interesting. Other question, so I already mentioned it a bit in my talk, this post-training. Have you tried taking a Quen model and just fine-tuning it further on German data? Does that work? Does it collapse? Does it explode? What happens?
Yeah, it definitely works. There have also been other groups that showed that this works. It works. We basically had this academic idea behind it as well to analyze what actually happens if you pre-train on German and to make it transparent. This works. Actually, our models, there have been a few models in the benchmark where we also compare against these fine-tuned models, and our 7 billion parameter model outperforms, I believe, all of them, even those based on Gwen, Mistral, and Llama original multilingual backbones.
Is that because their German fine-tuning data is worse, or like if you've used Quen 2.5, Quen 3, and on your data?
It's difficult. They don't fine-tune on that much data. They only use, I believe, 65 billion tokens, which is in the grand scheme of pre-training, honestly nothing. So I believe if you initialize from a multilingual model, you could get better scores, yeah.
Thanks.
Further question, yeah.
Yeah, thanks a lot for the very impressive talk. Are you familiar also with the Swiss initiatives with EPF, ETH? They also trained like a transparent model, this upper tooth model. That what is the similarity between your model and their model? Is there anything that that we can learn from each other to push this further forward? Or?
Yeah, I haven't looked into it in that much detail, but I believe it's quite similar. I believe they're also quite open, and they trained a 70 billion parameter model, if I'm not mistaken, right? It's a bit larger, but the idea, I would say, is the same. The difference is we were first.
But I think this is really very, very good. So all the other like large models, of course, most of them that there's a big company, this commercial purpose behind it. So in the future, what kind of application or where do you imagine this transparent model where, for instance, more like driven by university or at least like no profitable institute behind this? So where the case is that those models will actually play a very important role.
One more difference I just noticed, I believe the Swiss apparatus model is multilingual, right?
Multilingual, yeah.
Yeah, okay, this would be one of the other differences. Where this might be important, we believe that making this transparent actually helps using it in downstream applications. Meaning, if your language model does not perform well in a specific task, for example, you can actually go into the pre-training data and see and understand whether the model actually saw anything that might resemble your task during pre-training or learn something about your domain during pre-training. So if your model is not good on a specific task, you can understand why this happened and basically debug this, if this was your question. Yeah, okay.
Yeah, there's another question.
Thanks for the presentation. There's another project from European Union called Open Usual LLM, and what's the relationship between your project and that large language model?
A personal relationship, like none, none at all.
Okay. And I saw that you're still using the German Wikipedia language, German Wikipedia pages as one of the major sources. As the pre-training materials. And have you done some like data cleaning? Because, well, for German Wikipedia page, that's a pretty, quality-wise, it's pretty high compared with some other languages in Wikipedia. But still, maybe some bot-generated contents. Have you done some data cleaning of that?
No, not at all.
And that's not causing any issues or like a pollution or?
Not that we are aware of, no, none at all. And yeah, honestly, the idea was to play this entire German pre-training pipeline from scratch, just taking whatever is there and see where this gets us. So taking the German datasets that are available, using them, seeing what German chat tuning datasets are available, using them, and so on. So basically, if something comes up, this would make it, I would say, understandable that this is an issue. So this was the goal. So you could now look at this, but we did not do it.
Thanks a lot.
Anyone else? Yeah.
Hi, thank you for the talk. Does your model understand the German tax code? I mean, that's just a joke, but...
Yeah, funny you ask. Somebody in Erlangen actually tried this on his, I didn't get it, tax project he was working on, and he said it just completely aced it and blew all other models out of water. So
that's great to know. But on a more serious topic, so Germany, like German, I know that Wikipedia's German database is the second largest on the Wikipedia website. And German, like the language itself, is quite widely used, I guess, population-wise, but the vast majority of the text online is in English. So I'm just wondering how this lack of diversity, even though German is one of the biggest languages, affects like the performance of the model, and maybe you can provide some insight regarding creating a similar LLM for more minor languages, like Slovenian or something very exotic like Navajo or so on.
Yeah. This definitely impacts the model. For example, we asked it about computer science concepts like, I don't know, red-black trees or binary trees, and the model was completely lost because it had never heard of these concepts because they're only ever explained in English on the internet. So it didn't know about any basic concepts in this regard. For even lower resource, for lower resource languages like Slovene, I would say you don't need as many tokens as we have used here. We overtrained the models completely. Like we put, I don't know, I believe 1.3 trillion and then unique tokens and overall 3 trillion tokens into the 120 million model. This is way too much. I think you can get away with much, much, much less, and I think it's not that undoable as it is always painted to do.
And would you say this 1.3 trillion tokens that you guys managed to get in German, was it kind of, did you guys have to kind of scrape the bottom of the barrel, so to say, or were there still a lot of tokens that were
No, not at all. There is even a very much larger part which was labeled by Red Pyjama as tail, meaning low quality, and we didn't touch that at all. We looked at it, we scrolled it, and it honestly looked like regular text to us, so it should be usable, no issue as well. We tried to investigate this also in our pre-training ablations. So I think if you go to these sources, possibly train it, filter it a bit better, because there is some questionable content possibly in this tail data. I think you should get away with doing it with a much lower resource language.
Thank you.
So what I would like to understand is, like, particularly in line of this argumentation, is this the case that smaller languages, as they are typically called, will not have a chance to ever have a foundation model? Like, if you think about, like, for me, this is interesting because we really think about like robots everywhere in the world, and we're using foundation models to understand people, right? So will there never be a versatile robot for Slovenia or?
No, I wouldn't say so, because this is just an academic endeavor, right? So just like I said, in reality, if you wanted to build a product, you would use, I don't know, a multilingual backbone and then fine-tune it to a language. And what this enables is understanding what shortcomings might be induced by either pre-training or fine-tuning on this specific language. So what are the blind spots that this language is missing? And you can do that with any language, and I believe with as many data as you have, but then you understand what you are missing, basically. So if you would put it on top of a multilingual pre-trained backbone, you know where your blind spots are, and this is, I believe, something you should be aware of when you create such a model, or use it.
Yeah. And the other question I had is, like, I'm not so skeptical about translators, because they're really good translators. Right? So which role could translation play in this game, right? So, let's assume we have like a great corpus, like English or whatsoever, and then you translate this question to English, run it in that bigger model, and then translate the answer back, although sometimes it might be nonsense. But is this a better way rather than the other way around, that you make like translating English and then to a language and then learning a model? So what would be your...
I guess it depends from where you're looking from. If it's to be used by a German user, it might be, or who only speaks German in this case, it might be actually more transparent to translate everything to German, such that the user can understand where things might go wrong and be like, okay, this doesn't make any sense, and this is why my model doesn't talk sense. So I guess it's a use case question. I believe currently the translation models should be supervised in a way that humans should, if you want to train your chat model on this, humans should look at this. But in the future, we hope this is, you can just use your other languages to pre-train the model, but this is not where we are currently, I believe.
And then I had a question regarding this super cool scaling experiment as well, right? So, I mean, given your experience now, can you actually, would you be able to say, like, yeah, I have this model to train, like, what is the number of nodes that I would need, and where is it going to break? So can we do this? So is there any knowledge about this?
Yeah, there are various papers, I believe, that try to decode this, like chinchilla law, and I'm referring to this, yeah. There are various ideas about this, and they all have not really stood the test of time, I would say. I believe we have a rough idea of how to scale, how much you need, basically, but a lot of this was trial and error. But you can estimate this rather quickly. So you can just do a run for, I don't know, an hour or something, and you know how long it would take your training on this specific setup. And we did a lot of these runs to also configure our hyperparameters and so on. So while this is a very dark, obscure science, it is rather easily can be fixed within, I don't know, 2 to 3 days or something on your specific cluster setup. And then you know exactly how many tokens you will be able to use and so on.
Very cool. Thank you. Anybody else? Final chance for a question. Hey.
Thank you. I just ask one last question. So I think nowadays, I mean, especially like the AI change, I want to like ask your opinion whether you observe some interesting insight how this changes the artists, how they work. Like for instance, if we check about the AIGC, at some point people are afraid that they will take over the job of artists creating like drawings, pictures, but on the other hand, like these AI companies, they actually start hiring a lot of artists just to create like paintings, a unique style, just to provide data to their AI models, right? Because this can create actually new opportunities for them. Since you work with the professors or people from humanity, I want to check whether you have observed some new, like, you know, interesting way that they see this whole AI use language, because I mean, Wikipedia very soon will squeeze everything out of this, but in future that maybe the people who write stuff or we document not only for human to see, but for data more for AI, right? Then the way we create, summarize our new knowledge might need to change, or actually somehow this may be also change in the future. Have you observed anything, or how people working in their field see this right now?
Sorry, the last part of the question?
So how for instance, the people, the professors working in the humanity, that basically they work in the natural language used to actually create, to teach human, to summarize our knowledge for human, but now maybe there's new opportunity to summarize this just to feed the data in the right format, the most interesting format to AI models, right? So what is there any like a new change in their field?
Yeah, definitely. The chair we are cooperating with is very actively pushing in this direction of using these models for their research, right, and for their studies and so on. So this is actively happening, and they even came to us and said, okay, let's do this. We want to have this model for our purposes. So yeah, definitely.
Thank you. Thank you.
Then let's thank the speaker again. Thanks a lot. We're coming to the final presentation in this session. Before I introduce the speaker, a brief announcement. We will, after this presentation, there will be a break, and before we enter into the break, we will have a group photo here on stage. So please don't run away, even if you are like in need of coffee or cake, whatsoever it is outside. Okay, but before that, we will have Christopher Mutschler presenting. He is a director of the Positioning and Networks Division at Fraunhofer IIS in Nuremberg, Germany. Before that, he was head of the Precise Positioning and Analytics Department and headed the Machine Learning and Information Fusion Group. He also was a chief scientist at the Locating and Communication Systems Department, also at Fraunhofer IIS. He also teaches at FAU, Friedrich Alexander University in Erlangen, where he also got his PhD from in 2014. Christopher, we are looking forward to your talk.
Yeah. So, thank you for the introduction, and thank you for inviting me. We heard two talks so far, both somehow related to vision and language. And today, in this talk, I want to talk about some other dimension. I want to talk about radio with you. And radio is something that's usually not very close to us because we actually don't see radio, right? But we are able to visualize radio. And this is very beautiful, right? Isn't it? So what you see here is basically the spectrograms of different jamming devices that are installed by truck drivers in Germany to actually get rid of paying the toll, right? So usually truck drivers go over the Autobahn, and by traveling over the Autobahns, they are tracked, and they are actually paying for their time on the road. And those guys are not stupid, so they install jamming devices in their cigarette lighters to actually jam the signal, and the location cannot be like really estimated, right? And you see that there's different types of devices, or actually different signatures those devices are actually producing. And you can work with that data using AI methods and machine learning, and you can detect those on the bridges. And if you detect them at the bridges, you can actually estimate a fingerprint from them and track those signals as the truck drivers follow the routes throughout Germany. And then you can actually take them out, right? So this is something that you can do with radio signals. And when we talk about like video or LiDAR data, usually in robotics, the question now arises, or the question that I'm dealing with is, can we use like wireless networks? So this was a GNSS example, but can we use like wireless networks that we use here, like our Wi-Fi networks or our 5G systems? Can we use them as like general purpose sensors that we can make use of in order to perceive the environment, just like we do it with RGB cameras, LiDARs, and IMUs, right? So that's the question I want to try to answer today. So the question is, can we build a sensor from the wireless network? And usually I will talk about localization. I will skip all that and try to, without giving you too much detail into communication theory, why does a wireless communication channel look like that, all right? So usually you have some transmitting device and some receiver units, like in your Wi-Fi system, your smartphone and your Wi-Fi routers. And usually everything starts with the communication. So a signal is transmitted from one point to another. And as the signal actually traverses the environment, it interacts with the environment, right? So you have here a signal that is coming from the transmitter in the middle here. And basically the signal is received by two receiving antennas, might be two Wi-Fi routers on the direct path. And the signal has something like a shape in the time domain, and if you correlate on that signal, you get actually something that looks like this. And what you see here is like a clear peak. Yeah? So the signal is really detected at this point in time at this Wi-Fi router. And of course, there's a lot more in the environment. There's a lot of like metallic surfaces. Like the wireless signal gets actually hits those surfaces and gets reflected in any direction. If it's not like really meaningfully reflected, the signal gets scattered and leads to a lot of noise. This is what you actually see here in the other part. So this is actually the part that gets scattered from the signal part that is scattered from the metallic surfaces. And there is maybe, hopefully or not hopefully, also like really large metallic surfaces, which actually do not really scatter the signal, but sharply reflect them, like a mirror, right? If you have a camera and you have a mirror, you actually see the reflection in the mirror. From an image, right? And you also see that in the radio signals. And if you have something like this and you just look at what's received from the radio point of view, at this receiving unit, the signal might look like this, right? So you have like a peak for the direct signal, but the direct signal is blocked, and you get maybe this reflection, maybe another reflection, and then you get a signal peak here. And we actually want to make use of that in order to formalize this only roughly a little bit. So let's define the channel. So what I just described to you can also be, of course, somehow formalized. And we describe a channel like this. It's like a transfer function of a signal that travels through the environment. And it basically contains certain components when it is received at some antenna unit. And it has basically the direct signal part, which is basically the strongest thing that you can get. So the signal is really like traveling from a transmitter to a receiver. So this is this thing. And then you have like a couple of reflections, maybe none, maybe even more. And then you have some signal components that can be just considered as noise because you cannot model them, right? And usually what we measure when we actually look at the signals, we measure something like this, or we approximate this. Because we have a noisy sensor that is limited in the bandwidth, so we actually do not like see a full resolution. We get some like quantized version somehow of that, right? So we approximate this. And back in the days, maybe if you want to do emitter positioning, so maybe if you want to locate where the smartphone is actually located, you would be interested in this direct path, because if you know the direct path, you can actually measure the distance with the time of flight, so with speed of light, and then you can actually trilaterate the position, right? So if you do that for many things, you can do that. But I don't want to talk too much about positioning today. So let's look at the wireless channel when some persons are moving in some laboratory environment. So this is a student of us. He's actually walking through the environment. He does actually not carry any emitting devices, so he doesn't carry a smartphone or something. What you just see here is how the channel, which actually the communication channel between these two antennas here, so there's a receiver and a transmitter, how this actually changes as the person moves through this laboratory, right? And it doesn't even matter if he carries a transmission device or not. For the first part of the talk, I will actually consider that someone carries a tag. But what we actually can do is we should work with that data, right? So we could actually treat this signal components that we receive here as something like a characteristic fingerprint. This is a characteristic fingerprint for this situation in the environment. And we actually want to use that to estimate some, in this case, maybe a position in the three-dimensional space, like you would do it with a LiDAR sensor or with an RGB sensor. And you can make, of course, use of very rich architectures like CNNs or transformers. And of course, you should also make use of how the channel evolves over time, right? So you see that things are moving. And of course, you can take the evolution of the channel to track the position over time, to do SLAM, to learn the representation of the environment, things like that. We've actually shown that in the past, that you can do things like that. So in this case, of course, we do. In this case, we did emitter positioning. So we had a device that actually communicates with the Wi-Fi system in this example, for instance. And you just try to locate this device, where it is inside the room. And what you can basically do with some pre-processing of those signals, here you see such a signal as it traverses through the environment. You see actually that you can take those signals received at several antenna units, and then you can actually learn something like a neural network to actually fit the parameters in order to do the mapping from the raw signal data to a labeled position in the environment space. And this works also pretty well. If you do that and if you compare that to traditional approaches that you, for instance, know from GNSS, this is where you can actually get. So what you see here is two approaches. On the left side, it's like a classical approach to do location, basically meaning you measure the distance between a transmitter and an emitter, and then you do triangulation or trilateration of the position, like drawing circles and looking for the intersection of the circles, right? And on the left side, you see that this doesn't really work well in industrial scenarios. You have a lot of reflecting parts, so this is like a reflective corridor. And if all your signals get reflected, it's very hard to measure the distance between the signal doesn't traverse on the direct path. It takes some routes through the environment between the transmitter and the receiver, and you overestimate this distance, right? So if you do that, probably the system isn't working reasonably well. However, if you apply like CNNs or transformer models on the signal domain and you train against the data set, then you can actually achieve a performance that looks like this. So it's reasonably greenish in every part of the environment, and you can actually, in that area where everything is fine, where you can actually see everything is good, but also in that area where usually the classical systems, they completely fail, you can actually do a robust positioning of the emission device. So this was very early work that we did some years ago, and my introduction was I want to build a sensor that we can actually use in industrial setups. Like we want to track forklifts, we want to know what's happening in the environment, and what I didn't tell you, our sensor needs tons of labeled data to do something meaningful, right? So if you don't have the training data with the labeled position, we cannot do anything at all, right? So we must approve this. So at some point, we need to make use of channel data that we can measure or somehow do it in a more clever way to actually get our sensor running. And so the basic idea is learn as much from unlabeled data in order to build up the sensor, right? So imagine that in the current scenario, we had a lot of signals, and we have all these readings, and we have a regression. We defined a regression task. We had a lot of data and their corresponding positions, and we learned this mapping function, right? The thing is, obtaining those labels is very expensive. Where do you get them from? Usually you need something like a reference system. But this is maybe not what you want in practice. What you can get is a lot of unlabeled data. So you can just have your communication system running, measure everything what you do here. You can just record it, right? You don't have any reference positions for our devices, but you have all the data. The question is, how can you make use of that data in order to get the sensor running more quickly, so do the positioning task or the sensing task more efficiently? And that's an idea, basically, that we call radio foundation models. And it actually takes up a lot of ideas that we already heard today. I will maybe not go too much into the details because it shouldn't be a communication theory seminar here. By the way, the question is, how can we actually make use of unlabeled data to actually learn an efficient representation of wireless signals in an environment so that we have this efficient representation and then can actually take only a few labeled data points to use this representation to solve the localization task, for instance. We did that using like a 0.5 billion transformer model where we actually defined a masking task as a pretext task, meaning that we took all the channel data as an input, and we generated, what we actually did is we cropped out randomly 50% of all the channel information, and we tasked the model to actually reconstruct the masked parts. So we actually generate the data or the target data from the unlabeled data. And by doing that, basically, the transformer model is tasked to find an efficient representation to actually reconstruct what's there. If you imagine that, for instance, you have several access points located in the area, and you have like all those peaks in the signal, and you crop out some of them, basically the model should be able, from other information from the other access point, be able to reconstruct those missing peaks. Right? So it's an overdetermined system. It should be able to reconstruct it. And basically we had some transformer model. We learn everything that you usually know from transformers. We have an attention layer, positional encoding. We actually reconstruct in the frequency domain. This is a slight thing to make it more robust to certain variations. And then what we usually do is like here, what we also have seen before, we regress or we fine-tune the model on the classification token, meaning that with a little bit of like labeled data from the environment, we can actually use this pre-trained representation, the transformer model, to actually use it to do the positioning task. And if we do that, so this shows the result. So what I told you before was something in that domain. So this is basically different ways of estimating a position from raw data. And what you have on the x-axis, you have the number of labeled data samples that you use to train your model. And on the y-axis, you have the location error in the two-dimensional space, so the 19th percentile of it. And what you actually want to do is you want to push this thing down, right? So you want, with little training data, you want to have a good performance, meaning low localization error. And what you see here is actually that only with like roughly 500 labeled samples from the environment, you can actually already get a sub-meter accuracy, right? And you also see that this model is actually also working if you like change the environment, put up a different setting here in the environment, and you can still use the pre-trained model to actually fine-tune with real data. Exactly. So there's also some follow-up work that we just now submitted to ICLR, where we actually try to learn this representation like more efficiently. So in the previous thing, we just masked out from the signals parts that are tasked to reconstruct. And there is an assumption in the communications theory that's called compressed sensing, meaning that we have a complex high-dimensional channel data, but everything that we see is basically coming from a few underlying factors plus some noise floor, right? So what we had in the beginning, there's a lot of things that is considered noise, and there are a few things that are actually determining how the signal looks like when it is received, right? And this is actually what we try to uncover here. So we actually task a transformer model to use a sparse-gated autoencoder to really use only a few dictionary elements, so like parts in the environment that are really like important for the signals and how it is actually reflected. And we task it to use little factors in the environment to reconstruct signals at a receiving antenna. And that's now our task in this work. And by doing that, basically, we even outperform our previous model. So what you see here is on the left side, I don't consider the right side too much now. So on the left side, you see this location estimation problem, so actually tracking something like a robot. And you see that the masking objective was this. We actually trained it on different publicly available data sets. There is unfortunately not much of them. And we had several baselines, and you see that with that model, actually we were able to not only outperform our previous approach, but also the other recently coming approaches. Okay, so maybe at this point, I'm again, I guess, already halfway through the presentation. Let's change gears a little bit. And I want to take the rest of the time to give you an idea that is called basically channel charting. So what we did so far is we did a lot of assumptions, right? I did not explicitly mention those assumptions because everything was clear. But maybe let's put them down. So our basic assumption was that so far we have something like a two-dimensional space. I don't talk about three dimensions so far, two-dimensional space, and we know that some transmitting device, like this one here, is somewhere in the two-dimensional space, right? So like on this sheet here. And what we did is basically, we had this channel information that we get from all the access points, and we tried to learn a mapping from this high-dimensional channel representation, which is much, much higher dimensional, to this location, which is basically in the two-dimensional space, right? And what we also talked about is that the environment uses something like a mapping function. And the mapping function we call the channel, right? And basically the input to this mapping function is something like a Markovian state, it's called X, where the actually emitter is currently located. And then the environment actually uses this mapping function to generate the channel data. And what we basically see, or what we did not really use so far, is that basically what we see is the manifold on which the channel information data works on. So this is like a very high dimensional space, and it's basically something like, if this is a piece of paper, this is something like a crumbled piece of paper, right? And the CSI data, or the channel data that we used, is somehow living on this space, right? And the question is, if we only use some of these sample points without any information of P of X, can we unravel, can we actually fold up this paper, right? So we have all the measurements on the paper, let's just fold it up, okay? And then it's maybe two-dimensional again, right? So in a sense, this means, can we find the inverse to H, right? From the CSI, can we get to the position? How can we do that? If we actually could, if we perfectly had a digital twin of our environment, so we know everything like geometry, reflection parameters, and we actually defined the Maxwell equations and radio wave propagation, we could actually invert it. But maybe it's not even necessary to do that. At some point, so if we knew the environment, we could do that. And the slides that we talked about so far, we somehow approximated it, but we didn't really unfold the paper so far. And that's the idea of channel charting. And I give you only in the remaining 5 minutes, I will give you a short idea how this basically works. So what you see here is the environment we are living in, or the environment actually we did to generate our data. And what you see here is colorly encoded, something like the distance between two points. So if 2 points are very close in the Euclidean space, their color is also similar, right? It's somehow the color gradient encodes somehow the area. And the basic idea is to have something like a representation, and we have something like, what we basically do is we take 2 of these inputs, say we have 2 channel measurements at 2 close by locations, right? I have my smartphone here, and I have my smartphone here. And what we basically do is we take both of these measurements, put them in something like Siamese neural network, or let it be something different, and we reduce the dimensionality into a two-dimensional space. So basically, we do all what we know, and we do it in a two-dimensional space. And basically, what we want is that the distance between those two-dimensional representations down here should be somehow similar to the distance that we had in the high-dimensional space here. So if we find a mapping that actually satisfies that, and we take a lot of pairs of measurements, we actually find a mapping from the high-dimensional channel state into a small-dimensional, two-dimensional state, which is basically the unraveled piece of paper, right? The question now is, we can calculate this distance. This is a x and y coordinate here. So here's x and y. We can calculate the distance. How can we calculate the distance between those 2 points? And actually, so if we put in things that are dissimilar, also this distance should be large and this distance should be large. We can calculate this distance. Question is, how does this distance look like? And in the paper we actually had last year, we have shown that we can actually calculate a proxy of the distance in the high-dimensional channel state that is actually locally consistent. Meaning that if you have a channel measurement here and you have a channel measurement here, we actually have proven mathematically that you can actually subtract those 2 signals from each other in the bandwidth limited case. And this subtraction gives you a reasonable proxy for the real world distance in some arbitrary metric. And the error that you have on this distance is actually upper bounded. And if you do that, and if you have something like a proxy distance here, you can actually train this network, right? I have a pipeline for that to give you maybe an idea how this looks like. So what we did is, we had just people running with their smartphones through an area, right? And we just collect the channel data. So the smartphone just only communicate. There's no reference system. And what we basically do is, through these local distances, we actually take arbitrary pairs of points from the data set, and we actually calculate the distance between those 2 measurements. And this can actually basically done in order to find distances that actually traverse paths between those 2 measurements. So if you have a measurement here and you have a measurement over there, you cannot just subtract those 2 signals. However, if you have a lot of measurements in between, you can actually sum up those differences. And this gives you a reasonable proxy like for the real distance between those 2 points in the high-dimensional space. And if you do that, you can actually learn a neural network just like this. And if you maybe probably see it, or I don't know if it's really the case, you see something like the unfolding of the manifold, right? And this is what you then see. And then if you take some additional information, something like a coarse map, then you can actually like really get a nice representation of the map. And then you can do positioning within that map without having a single labeled data point. You still have to somehow define your coordinate system, yes, but without a single data point, you can do positioning. And to actually go a little bit further, I also told you about this in the first. So this is actually the video that we had in the beginning. I guess there's a video, exactly. So in all the previous cases, we actually actively located a device, right? So this thing was sending something. What you see here is this guy doesn't carry anything, right? And interestingly, what you see is if you have a transmission system like this, like a Wi-Fi access point here and a Wi-Fi access point over there, they exchange information all the time. And actually, by just walking through the area, you will change what those access points are actually measuring, right? And it turns out that you can actually use the same method of channel charting that we introduced before to do a passive localization of objects that don't carry anything at all, right? Same thing, you have a data collection in the beginning, you unfold, you unravel the manifold, and you do a positioning of passive objects without carrying anything in an unknown area, without any labeled data set at all. Okay, maybe, I don't know how much time do I have?
5 minutes.
5 minutes, okay, and then I can maybe also...
including discussion.
Okay, then maybe I will just talk about one point, which is always, if you go really, so we have now our sensor, and it's really sensing the environment. You can use radio to actually sense the environment, but still you want to have this maybe working in a smartphone. And big transformer models, it's maybe a hard thing. Turns out basically that you can also like efficiently compress such like sensing-based fingerprinting models using classical approaches known from hyperparameter optimization and model pruning. So what you see here is like examples that we had that you can actually prune a lot of parameters from the neural network. Of course, there's a trade-off between energy and memory and like predictive accuracy. But you can actually define a very nice trade-off to actually compress those models to really let them run on a smartphone or on a local robot where you don't have like a GPU cluster attached to it, right? Okay, so if this includes, then I will actually go farther on this one and go straight to the summary slide. So what's next? Maybe you also know that, but wireless data is somewhat, or my impression is that wireless data is somewhat less accessible to AI ML researchers because you cannot see it and it's very complex. It is in the complex domain. I omitted a lot of things today also, but I think that there's a lot of potential. So we had also this year on ICML, we actually had a workshop on wireless communication networks, and there's another one at NeurIPS too. But there's so much more to do because it's actually, the domain is not easily understandable, but all the methods that we know can actually transfer to the radio domain as well. And the wireless network as a sensor could be an additional modality just like vision today, right? So you can just use it, it's there, and you can work with it. And at its core, you usually use AI in order to do anything meaningfully within the sensor. That's it, that's my references, and then we'll conclude maybe here. Thank you.
Thanks a lot. We have time for a few questions. There's... Yeah, he's on the way.
Thank you, Professor, for your very interesting presentation. I'm coming from optical product line. We sell our Wi-Fi product to the whole world. So first question is, we are now researching the home robot. We want to combine the Wi-Fi sensoring to the home robot, and we need the robot to follow the people to censoring the breath and heart beating and sleeping quality. And we want to hear your opinion, comments about this use case. And the second question is that you mentioned the radio fundamental models. We think it is a very great idea that may be possible to solve the generalization problems. My question is, how, if we have very few data, how to build these fundamental models?
Okay.
Thank you.
Yeah. So thank you for the question. So the first question is a typical use case that you also hear a lot if you talk about 6G or something like that. It's basically like breath monitoring or hospital things in the hospital to monitor patients. And what we also need to say that there is a lot of trade-offs in the communication system. I didn't talk too much about it, but there is carrier frequency of a system. For instance, Wi-Fi is operating either in the 2.4, in the 5, or in the 6 gigahertz frequency spectrum. And if you usually talk about things like breath monitoring or heartbeat monitoring, you usually refer to systems that are operating at much, much higher frequencies, where you can actually have a much, much higher time resolution. So this is something that I didn't talk to you about very much today. If you use an RGB camera as a sensor, usually you get a full HD image of the environment. There is maybe occlusion and there's maybe also exposure things, but then the radio domain is much more complicated. Basically what you get in really systems that are installed here is really systems operating on low frequency with very narrow bands, only 20 megahertz, giving you an indicator of the time resolution. 20 megahertz is not that much. You cannot distinguish many things. And usually if you talk about heartbeat monitoring, you're usually talking about things working in at least 70 gigahertz, carrier frequency, and also a much, much larger frequency band. So there is also work submitted every once in a while to ICML and NeurIPS, who do actually, with custom off-the-shelf Wi-Fi routers, a complete pose estimation. This is only this is a very academic setup, right? So the data is a little bit I wouldn't say crappy, but the procedure of how these things are trained and evaluated cannot really be applied to the real world. So my honest answer would be to make that really applicable in practice, to give you something like a benefit in the real world. It takes some time, and it also takes some technical advancement. So you cannot do that probably not with Wi-Fi in this range. There's also Wi-Fi in the upper range. You can, of course, do that, but you will not be able to do that with the Wi-Fi you are now operating. And the second question was about the data for the radio foundation model, something like that. It was about generalization, or about?
About the data. If we have very few data, how can we build the model?
Okay, so usually the thing with the data in the radio foundation model, it was not an issue that much, because usually to train or to pre-train the transformer model, you don't need labeled data, right? So you just need to set up your communication system and let it run. So you just like if those people here would want all the data that is actually captured all the time, they could just have it for free. This data really, like the data acquisition is not really like costly in any sense. The only thing so the system is running, it measures because actually it serves the purpose, you connecting with the internet. And that's the main job, and you just store all the data. The only thing that you need to invest is data storage. And usually it's not that big of an issue. So what we also have shown is like in a sense of like generalization. This is also a fact, because actually if you have the environment right now, it will look completely different when we go to the dinner in the evening, because people are not here. So the channel that you would observe from the smartphone lying there would look different today in the evening. And this is an issue. You have constantly changing channels. And this is maybe more an issue. And we have shown that you still need, in the transformer example where you actually need labeled data, you still need a little data. You need to update your model continuously in this setup. This doesn't hold for the channel charting example, because there you don't need any labeled data. But you constantly need to somehow get new ground truth input for the transformer and to keep it on track, because the wireless channel somehow also fades over time. I hope I answered this question partly.
Thank you.
Yeah.
Okay, we're running a little bit short, but there's one.
Very fantastic presentation. And I'm also from the optic product line, and I'm also engaged in the long contact breath and heart beating detection area. So I saw that you give me a very good example. That is but I have one question. So that in the densely populated area, and there's so many Wi-Fi signals, and there's how to deal with the interference of the wireless signals transmitted by different independent routers, especially in the same physical wireless channels. Yeah. That is the first question. Yeah. Does the accuracy of the positioning result will be influenced? So that is the first question. So, and the second question, that is maybe a discussion. So that is we see that the final signal that consists of three parts, and that is directivity and the reflectivity and also the direct diffractivity transmitted, three parts. And is if we focus in the first part, that is directivity, and that will be much simple, and that can partly solve this question. So that's all.
Yeah. So maybe the question about the interference first. I mean, interference happened at two levels. So the first one is, if you consider now a communication system. Usually a communication system usually solves interference using different channels or different frequency bands for certain devices. And if we now consider to do like channel sensing or sensing in general using a communication system, usually the communication system takes care about that interference is not happening. So in the Wi-Fi signal, you usually do something like listen before talk, in order to actually reduce the number of collisions in the channel. And in 5G, that's completely different, because you actually have a network that's actually like scheduling all the access to the radio access network. So we don't really talk about, if you talk about like doing that with like communication networks as they are, we don't really focus on the interference issue because it's usually detected by the communication network. If you do like localization by design, so you have a system that's there for doing sensing, then you really need also to take care about the interference because it can also destroy your processing pipeline. So if it's a thing like if you train, we also have seen that, if you train with data that is like you have a single transmitter walking around, you generate data and then you train a model, and then you try to apply it with many, many other devices there as well, they have a nearby effect on the measured channels. And the best way is to really have a diverse data set and to train it in the model. That's how we did it. Or you can also break up the pipeline and do not an end-to-end learning approach, but work on the signals, identify them, maybe curate the signal automatically. This would be one way of doing that. I hope this goes somehow in the direction of the question. And the other question was the discussion question.
The second question is that related to something like a discussion. So that is the wireless signal consists of 3 parts. So
yeah,
that is,
so this one.
Yeah, so that, can we focus on the first part that is a directively transmitted signal? So that we are
if you can focus on that part?
Yeah, yes, that is we can ignore the reflectively.
Yeah, exactly. Yeah. This is basically, there's a lot of work in that. And in order to identify all the other parts, in order to get a good estimate of the green part of the first one, this is basically where wireless localization has investigated the last 20 years. Maybe we can talk about this in the coffee break, but we also had a lot of work in that too.
Oh, thanks.
Great.
Thanks a lot. I think we need to finish right now. First of all, thank you again.
Thank you.
And then I was everyone to quickly come to the stage to take a big group picture, and then we will go for a break until 3:20. intelligence. And this is why I invited him over here to put some spices into the discussion. Oliver, let's go ahead.
Thank you very much. Thanks for warning everybody. And by controversial, you mean that I'm right. Of course, right? Yeah. Intelligence was once believed to be something that's unique to humans, but we now know that intelligence is something that we experience all over the animal kingdom. You see here four examples of this, with humans, with chimpanzees, with goffins, cockatoos, and with sardines and a marlin. All of these things have something in common, right? That's why we call them intelligence. And so there should be something that all forms of intelligence share, including artificial species, including artificial forms of intelligence. And so let's look at the bottom left here. This is a goffin's cockatoo opening something that's called a lockbox. It's a mechanical puzzle that, when solved, reveals a food reward. Let's zoom into this just so that you get some idea for how behavior biologists and comparative psychologists and cognitive scientists study animal intelligence. So here you have a acrylic glass door with a cashew nut behind it. In order to open the door, you need to move this lever. To move the lever, you need to rotate this disc so that the pin and the slit align, so that then you can remove it. But rotating it, you need to first remove this cylinder because there's a pin that is preventing rotation. Obviously, to remove the cylinder, you need to remove the screw, and to remove the screw, you need to remove the pin. Okay, all of you knew this, of course, and goffins, cockatoos, with the brain that's about the size of the tip of your little finger, can also solve this. So I would say that's intelligence. This idea of using a mechanical puzzle is used all over the animal kingdom. You see here again the cockatoos, you see a raccoon, an elephant, and a mouse. So this is kind of how we challenge and study animal biological intelligence. There has been recently lots of excitement about having artificial intelligences that also exhibit something that we call intelligence. Let's see how we test them. So here are some benchmarks that are being used to test large language models, for example. The first one is kind of a math problem with language and numbers. Well, if you Google this text, you will find 200 solutions for it. The next one is a very simple visual task at which actually large language models are only so-so. And then the next one is kind of planning problems, but for these also most solutions exist on the web. So if a language model trained on everything that you can find on the web solves these things, that's maybe not that surprising. So maybe we're not challenging large language models enough. And what would be more, kind of an obvious idea than to use the lockbox with a large language model? Okay, and this is exactly what we did. Here you see our roboticized version of the large language of the lockbox, and a robot that is driven by ChatGPT-01, which today is still the most expensive of the large language models, the thinking large language, if you want to use the API. It will explain what it's doing.
From the photos, there appear to be 4 separate wooden metal bars or plates with handles. X on the left with a horizontal handle, T in the center, also horizontal, A in the upper middle, horizontal, and Y on the far right, vertical. T seems to physically overlap with, or at least lie in line with X, suggesting it may be blocking X from moving. Because our target, X, is likely blocked, we first attempt to move T to free X. If T is free, it should change to state 1. If it does not move, it's locked, and another part, A or Y, may need repositioning first. This approach minimizes wasted moves by starting with the most probable blocker.
So this is
the puzzle appears unchanged
clever.
from the previous images, indicating T did not move and remains horizontal. No visible adjustments in the overall configuration.
So this is pretty clever,
suggest
right? It
T
continues
was
to
locked.
reason and it starts
Because T
modifying
stayed locked,
these
we
locks.
suspect
I'm going to
another
fast
part is
forward to a later point. This is the final step, well, at least according to the large language model.
In the new photo, the center bar, T, has clearly shifted from its previous horizontal position, indicating it successfully moved to state 1. A remains in its raised position, and Y is still pivoted. X on the left is unchanged. With T now free, the path should be clear for X, our target, to move. We will try to move X next to achieve our goal. In this new photo, the leftmost bar, X, is visibly shifted from its original position, indicating it successfully toggled to state 1. A remains raised, T remains slid over, and Y remains pivoted. With X now in state 1, we have met our goal of moving the leftmost part. The puzzle appears solved, and no further moves are required.
Now we tell the ChatGPT that it's wrong and that actually it
This
failed.
latest image still shows X in
And
its
it tries
shifted
again
state 1
and does the same thing.
along with T, A, and Y in the positions we set them.
So
there's no visible change.
I have to say that the first part really, really impressed me. It's really amazing. But then I was completely unimpressed by this. I mean, if we tell ChatGPT you didn't solve it, then I feel like ChatGPT should at least take that into account. So no matter what, I guess we're not there yet, right? So let's see what's the path towards solving this. One point of reference that everybody agrees to is that we need inductive biases, right? I think this is beyond question. The need for biases in learning generalizations. This is from 1980, right? And it says that basically biases are necessary for the inductive leap required to take data and to really generalize to new things. So let's take that as a starting point. And the question now is, do we get there through what I call principles, or do we get there with scaling laws? The notion of principles comes from the cluster of excellence that Wolfram mentioned in the beginning called Science of Intelligence, where we've developed kind of a theory of intelligence that involves these principles. These principles have been validated in a dozen disciplines, in probably 60 research projects on probably 10, 12 different species, and in all kinds of different settings. So I really think that there's something very interesting here. But before I get back to that, let's start looking at this lockbox paradigm. Here you see a synthetic lockbox. There are sliders. There are 5 of them. And the numbers indicate the number of the slider. Well, I guess there are 6 of them. And the arrows indicate the dependencies between the sliders. So this is a more complicated lockbox than we gave to the birds, because there's a dependency structure represented in this graph that is not visible from the outside, that a human or an animal or an AI needs to figure out in order to solve this. We've tested many, many humans on this using a haptic device, and you can see a short video segment of this happening here, where a human is playing around, moving the sliders. Every attempted action costs them some money, and whatever balance remains, we actually pay them. So we tested, I think, 300 humans with this. But we also made an experimental setup where an artificial agent is interacting with this, and obviously we give it instructions on how to do this, and it's getting, as an input, either a screenshot or the ground truth. So here we're actually going to use the ground truth. The bad news is that old models, and with old I mean from 6 months ago, do really poorly. I mean, it's laughable, right? They really do poorly. You see here on the x-axis batches of games that are played consecutively, and on the y-axis you see the steps that are required. You see that humans start low and get lower as they learn how to play the game. Gemini 1.5 Pro and ChatGPT 4.0 Mini don't do very well. But there was a surprise for us when we started taking the current generation of thinking large language models. So here, this graph might be a little bit difficult to read. Let's see. So let's look at the top left. Blue is always human, and basically you see here the first game, second game, and so on. This goes on. So this is time going upwards. You see on the x-axis the number of steps required, and you see here the distribution of how many steps humans needed in the first, second, third, fourth, fifth, and so on game. So you can see that the distribution was very wide for the first game. The mean was pretty high, and the variance was very high. But as the humans gathered experience, their mean shifted to the left, the variance got reduced, and you see a kind of a peak distribution. This means the human is learning the game. Okay? So let's look at the others. On the top right, we have Gemini 2.5 Pro, which basically isn't doing particularly badly, but the variance doesn't change, the mean doesn't really shift consistently. There's no learning. Nothing is happening here. The same thing is true for the others, even though you have to say that on the bottom right, for Claude Sonnet, actually something seems to be happening. It's learning a little bit, at least from the first to the second round, and the mean is pretty low. So something seems to be happening with Claude Sonnet that is not happening with the other large language models. Let's look at it. This is a medium example. Let's look at another medium example. Here, on the bottom right, Claude is really performing well, excellently. We don't really know why. But again, you see the same thing. You don't see a trend to learning. You don't see a trend to reduced variance. And if we look at the hard puzzle, where the dependency structure is very complicated, you see that again, humans learn, and there could be, if you're very willing to interpret something, kind of a hint of learning in Sonnet. In Claude, but really it seems like this is persistent, right? That these models don't learn how to play the game. So, this inability to learn from your experience, even though people claim that these models do that, I think is a striking piece of evidence that you can use to question whether these models already exhibit intelligence. And it's one of 6 problems that we identified with large language models. Due to time, I can only tell you about this. So, going back to the thing I showed you in the beginning, where we actually connected the robot and ChatGPT 01 to the real logbox. How do the results look there? This is the plot that is showing this. It's a little bit more complicated here. Basically, on the x-axis, you have the number of interactions that we allow the large language model, and on the y-axis you have the % of success. So if you only allow 6 actions, green is basically 01 using RGB as input achieves 40% success. So at least 40% of the examples that we used can be solved with 6 steps. But other examples require many more steps. So this is how the plot works, but you see that humans, or the human-inspired robotic strategy actually outperforms all of these things by getting 100% and by kind of having a steeper slope, at least after the first 8 moves. Now, obviously, the goal is very different here, right? The large language model is trying to solve everything, whereas this strategy only solves this kind of problem. But it still seems if we want to get to the point that we claim intelligence, we're going to have to at least kind of stand this comparison and outperform special purpose methods. Okay, so this is Usama Tsenkri, who is the person who did this work. And while you look at him, I want to summarize what I think we can draw as a conclusion from this. So there has been fantastic progress in large language models. The initial models that are 6 months old, they didn't perform very well, but there has been, especially with Claude, a huge step up. Now the question is this a huge step up on many problems or just on one problem? And is it coincidence or is it a really purposeful design in the system. What can we infer from this about the future of large language models? Will they be able to tick off all the problems that we've identified, or will there be a barrier that they hit? My experience is that there's the 80-20 rule, right? You can get 80% of the performance with 20% of the effort. And I think we're going to start hitting the flip side, where we need 80% of the effort to get 20% benefit, and maybe actually we don't make it. I mean, think of autonomous driving. I've been in the business for, 30 years. For the last 15, people have promised autonomous driving, and people are still saying it's almost there. So, the question is, where do we really stand? I think we don't really know. I've shown you one problem, the lockbox problem, which happens to be used in biology, but how much does it tell us about what's really within large language models? Difficult to say. What I can say is that I think large language models are very far away from reliably and robustly solving these problems. And you can draw the conclusion that you would like from that. Okay, if we now shift from large language models to general deep learning with reinforcement learning, I also want to make a comparison between principle-based and deep learning methods. Now, in this world, in the long horizon manipulation, embodied AI, robotic world, we're very fortunate that the people that do research on deep reinforcement learning have given us two benchmarks. Right? Two benchmarks that now everybody is trying to match. And the first one is called the furniture bench. And this is the paper that introduced it. You see also on the picture the idea that you have these 3D printed pieces of furniture that need to be assembled. Like I said, this is a benchmark that is not really solved. People need hundreds, thousands of demonstrations in order to get success rates of probably around 40% or so. I'm going to show you a principle-based approach that solves this problem from a single demonstration. And, due to the time, I don't have the time to go into much detail, but I'm going to show you videos. I'm showing you only uncut videos from demonstration to tenfold validation, 0 cuts, a clock in the background. I'm still going to jump around in the video, but if you want to look at the whole video, please come and see me. That was the demonstration. Now there's a processing phase where the robot is processing this demonstration to extract the right amount of information. And then there's an augmentation phase where the robot has left some questions and says, okay, that demonstration was nice, but it doesn't tell me everything I need to know. So this is the augmentation. Now it's a visual augmentation, but it also haptically explores things. And it uses this to augment its own policy. And once it has done this, basically I'm showing you 10 trials, successful consecutive trials for this problem. And maybe I'll jump ahead again to show you that we can do this even if we change the environment, if we change the orientation. So if we change the location where the table leg is put and so on. So from a single demonstration, we get more generalization than all the other deep learning benchmarks, frameworks that I have seen from a single demonstration. Okay, so that might be a coincidence, right? That I walked up to the student and I said, hey, have you seen this benchmark? Can you do it? And he came back 24 hours later and said, here's the video. Then I found this other benchmark. It's the functional manipulation benchmark that probably many of you also know out of Berkeley. And yeah, I mean, the same thing happened. We used the exact same method that actually was designed for something completely different. And again, we start with a demonstration. You can imagine how it works. There is, again, an augmentation phase. The same thing as before. The robot visually and haptically explores. And then there's a set. Now there's a little feature here, which is sometimes it fails. This has only happened twice in all the experiments we did. But if it fails, the human can give a correction. And this correction is integrated into the policy. And so far, we've never had a situation where you needed to give more than one correction. And so basically, you have a single demonstration, a self-guided augmentation phase, possibly a corrective intervention of the human, and you have solved a complex, long horizon, multi-contact or contact-rich problem. Yeah. So how does it actually work, right? And this is where the principles come into play. Like I said, I probably don't really have time to get into much detail, but let me talk about the first principle. It's separating general and instance-specific information, right? We get one demonstration, and obviously it contains general information and it contains instance-specific information, and only the general information can help to generalize. But how can we tease it apart? Well, this is where the principle comes in. The principle tells us exactly how to tease it apart. And it's very simple. It's based on environmental constraint exploitation. And if you analyze a particular demonstration using this view, using this lens, the information immediately separates into a generalizable, contact-based policy that applies beyond geometry, beyond instance, beyond friction coefficients, and all the stuff that you don't want in your policy because it disturbs your generalization. Think about the opposite, right? If you are trying to do this from data, you have, let's say, 100,000 of these demonstrations, and they contain all kinds of information, and you're trying to tease this apart. You're trying to tease apart which part is general and which part is specific. The only way you can do that is using your data, but we know that every data set that we can possibly assemble is biased in some way that is not aligned with the task. So we're prone to jump onto divisions of the data that are not valid. And this is something that we can avoid here using these principles. To give you one more example, here is a robot trying to insert, I'm not a coffee drinker, but you know, the thing that contains the coffee into the coffee machine. And the model has been changed, right? The model that the robot has is different from the model that's in the real world. And you can see here in green the true rotation axis, and in red the estimated rotation axis. And this shows the power of being able to extract the instance-specific information as you execute your general policy, right? So the general policy is completed interactively from sensor information to get the whole policy that you need in order to execute robustly. And so here, while it's inserting this thing into the coffee machine, it's also estimating the axis, and it's completing the policy, making it truly general. Okay, the student who did this, whose name is Jing Li. And again, I mean, while you can look at his face, I'll talk about kind of a comparison of principles versus data. Here are two examples where principles have beaten data on data's territory twice, right? We took their benchmark and we kind of solved it from a single demonstration. We have fewer assumptions, we have more generality. It's a single demonstration, not hundreds or thousands, not a single GPU involved. Well, maybe there may have been in the visualization a GPU. You know, CO2 balance is super small. This is an alternative approach to embodied AI that resembles much more closely the parameters of biological intelligence, right? You don't need 100 examples or 1,000. You can do it with 20 watts rather than, I mean, we've seen the watt numbers earlier today for learning the large language model. This is not how we learn language. We don't need thousands of watts. So all of this, I'm saying, I think principle-based AI is a really promising way to pursue. So, is it all a big misunderstanding, this debate that we're having about, you know, should inductive biases come from data? Should they come from principles, whatever? Is it? Let's look at this, right? This is Hans Moravec, and in his book, Mind Children, which I remember my dad gave that to me as a present when I was 14. I don't think I understood it, but now, I cite it all the time. He said, it is comparatively easy to make computers exhibit adult-level performance on intelligence tests, like the ones that we've seen that we test the large language models with, or playing checkers, or chess, or Go, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. I think our whole community has fallen for this, which is called Moravec's paradox, again and again and again. When Deep Blue solved chess, we thought we had solved AI. When there was Go, we thought we had solved AI. When we could generate text, we thought that we had solved AI. We keep thinking that we have solved AI, and I think we're barking up the wrong tree. Let me explain. This is another, I think, very interesting person, Leonard Savage. He was a statistician, he died, so he was a statistician. He wrote this very interesting book, The Foundations of Statistics. And Milton Friedman, who was an economist, Nobel Prize in '76, said about this man that he's one of the few people that he would unhesitatingly call a genius, right? Just so that you know, I'm not picking to support my argument some strange dude here, right? And in this book, he talks about, I'm going to wait till Tamim, but I can send you the link. Okay. So he talks in this book about small worlds and large worlds. And that sounds very strange, and I've spent hours and hours. He really is a genius. It's difficult to read. But the small world is a world where we can define a state. And like in chess, right? We know the state of the board. Where we can define the motion model. We know when you make a move what happens. Right? We know everything. It's kind of a perfect knowledge world. And then there's large worlds, which is the real world. And he argues that the only chance we have, right, and he made decision models from statistics, the only chance we have to address problems in the large world is to consecutively solve small world problems. I'm not sure he was right about that, but the idea is that right now, everything that we're doing is small world stuff. Chess, Go, language. Everything has this property that we can exactly define the states and that we exactly define how things evolve. And that is not what intelligence was made to do. Intelligence was made to have us deal with the world around us, with the large world. Right? And as long as we stay in the small worlds, I don't think we will have a chance to understand intelligence. And so I would, maybe as a last thought, submit to you that I think the principles that we're studying in this Cluster of Excellence Science of Intelligence are exactly the key to take large worlds and to turn them into small worlds so that we can actually solve them with the methods that we have. And so if you find this interesting, I invite you to go to this webpage because you'll find more information about it. It's all very new thinking, and we're still in the process of writing papers about it, so there's not really a very good thing written about it, but I'm here. I'm on time. I used 30 minutes, and I can answer your questions. So thank you very much.
A very interesting talk. Yeah, I have one question on your demonstration of the corrective motions. So you have showed the demonstrations by a human demonstrator, and then you have the corrective motion when the robot fails. So my question is regarding the corrective motion by the human demonstrator or the robot itself. So definitely, I can see for most of the time, it can follow the general planners for one point to another point. But for most of the failure cases happen in the cases when you have the physical interactions with the whole. So for that case,
the human demonstrator seemed to go for trial and error as well. So I'm wondering if the robot can do trial and error to find a better solution.
So I completely agree. So let me take a step back. So you can, the first phase is a demonstration, and you can view the two following phases as corrective phases, right? The first one is a self-guided corrective phase, where the robot basically, if I demonstrate this, right, you don't know, am I just moving through free space, or is there actually a surface that I'm sliding along with a very small force, right? That's just not in the data. So the robot can go and press and say, oh, there is something, and can move up and say, there's nothing, right? And so basically the robot can improve its local understanding of the demonstrated policy. But there are things that are ambiguous, which it cannot resolve from these local explorations. And that's where the human demonstrations come in. So your suggestion was to say, cannot the robot suggest them itself? I think this would be an excellent idea for learning, right? I think this is exactly the right place where learning should be injected into this approach. So yes, I mean, in the end, and actually I think that you might want to even use learning to generate the first demonstration, right? So I think that what I presented in some very strong sense is complementary to all the learning approaches that are trying to solve the same problem. This should just be integrated into the learning, and you can learn either the corrections or the original demonstration. But you shouldn't do work that you don't have to do in between, right? You don't need 10,000 examples if one is enough. Why wouldn't you want to be smart, right? But yes, there are, at both ends, opportunities for learning to help.
Thank you very much.
Yeah, hello. Also, thank you for the talk. So you made the distinction between this like high-level abstract intelligence and kind of the low-level physical intelligence. And you also said that currently most benchmarks evaluate like the first type of intelligence. So, in your opinion, what would we need to create like proper benchmarks for the physical intelligence? I mean, you showed one with a kind of this block world and so on. So, do you think this is sufficient, or like what components should we add to properly evaluate this?
Yeah, let me first comment on something you said in the beginning. You said high level and low level, and I think this is an apt way to view it. I'm just not sure about it, right? So I didn't say that exactly. I talked about small worlds and large worlds, and I actually don't know. I think that there's a continuum between them. So, for example, as the horizon of a task increases, maybe with longer horizons, you're getting more into the large world because planning this is much more difficult, right? So for Tower of Hanoi with 3 disks, large language models can solve it. With 300 disks, you're much better off finding an algorithm that solves it and executing that, right? I mean, why not, right? So, but then the second, the real question was about a benchmark, and this is an excellent question, right? I was at Coral last year in Munich, and every single talk talks about generalization. Right, generalization is AI, right? I mean, intelligence is generalization. This is the goal. This is what we want to do. But nobody knows how to benchmark generalization. So this is something that my group is right now really thinking about a lot, and we want to try to write a paper about it. So sorry. The short answer is I don't know. If you have ideas, I'd be happy to discuss, because I think that's really the key. How can we, right now the only thing I know is show you uncut videos, right? Where I go in and I disturb the robot and it still works and all of that, right? But we cannot all watch hundreds of hours of videos to be convinced that the method some other group has made is a good method, right? We need some other way. But I don't have a good answer yet.
Thank you.
Sorry.
I do have a question. What else? I mean, when I started working in this AI space, people were talking about this notion of AI completeness. It's kind of like taken from NP completeness. If you can solve one problem, you can solve every problem. Some of this notion has disappeared, right? But it is kind of like this, from my perspective, this generalization question as well, right? So, and my feeling always is like if you can solve one of these problems, then you have this understanding of the world that allows you to solve other complex problems as well. Right?
But is that, I mean, is that really true? I mean, a great question, right? I mean, it goes right into the depth of it, right? I think that all species that we have, let's look at biological species, right? Because there we're fairly certain that they're intelligent. They're all tailored to different ecological niches, right? So fish can swim without using a muscle, can swim against the stream, right? Just because of the way their body is structured. And if I try to throw the fish in the air, it would just act like a stone, right? So I think that even though we dream of this generality, like the universal Turing machine, right? I don't think that is what intelligence is about. Intelligence is about having a set of principles embodied and coded in an agent that lets it deal with a certain ecological niche. So generality is still in relation to a particular problem. Right? So the universal problem solver, that was one of the first things people did in AI. I don't think that can exist.
But aren't we humans kind of like able to solve these problems that you also showed without actually, even when I've never seen one of these puzzles, I have this built-in policy, at least try it out and try to find that solution to it.
Yeah, I think that humans are, among all species, probably the most general because they have these exploration strategies. And actually, this is where the lockbox problem came from, that we're doing studies with humans on what these exploration strategies look like. But obviously, the lockbox is tailored to the things we know. We know sliders, right? I mean, everything our world is tailored to us. If you go to a completely alien planet, it's unclear whether your strategies that you've developed on Earth would transfer to that planet. I mean, you would be able to probably learn strategies, right? So there's maybe some foundational things that allow you to learn, right? But I don't think that we are universal problem solvers. In our realm, we see it appears to us that we are, because we define the boundaries. But I don't know. Do you think we are?
No.
Okay.
Yeah. Thank you very much, Oliver. This is, of course, exciting, and I think I agree we need a better understanding of the principles of intelligence. But if we look a little bit back in the literature, so many people came always with other ideas, starting with embodied intelligence, morphological computation, and so on. But the difficulty is somehow to really bring this into robotics, right? These often abstract formulations of principles of intelligence. So can you say something based on your experience, actually? What should we do and what can we do differently or better in order to transfer these ideas and laws and principles to robotics?
So these principles are actually not abstract theorems. They're very concrete, and you can translate them directly into, this is what we're doing in my lab, right? We're taking these principles, and it has flipped. Maybe a year ago, it has flipped, right? That we were doing research to discover principles. Now we're using the principles to drive the research. The most recent example is a paper that appeared at ICRA 2015 that won a Best Paper Award for Planning and Control, where we took the principle and said, well, this should be able to generate robot behavior, right? And we generate robot behavior in a very robust way. And I think it won a prize because it's not control, it's not planning. People don't know what it is. We don't know what it is. We do now research studying that thing, which has 150 lines of code. We don't understand it. It's just like C. elegans, that worm that has 40 neurons. We have an exact map of all the neurons. We have no idea how that thing lives. So all of a sudden we build something that works as an engineering tool, but we don't know why, right? And now we're starting to study it like we're cutting open a worm to understand how it does that. So it's very, and give you another example, right? So I think that we're going to get to the point where getting insights into biological intelligence is going to be more efficient if you do it in synthetic tools. So, I showed you the sardines swimming, right? And people study how these collectives move, and there are very simple rules that describe how they move. We have found a way to take this principle that we're using, and we implemented that, and we can derive the rules that people have come up with to describe it. So we have the most basic explanation of all of these behaviors. Right? So the principle they have proven in all kinds of, in swarms, in robots, in all kinds of things, to be very useful modeling tools, right? And so I think we're using these things very, very immediately to do research.
One final question.
Thanks, interesting talk. And I'm curious, actually, a couple of months ago, actually, I studied a branch of AI called neurosymbolic AI, which is the hybrid architecture of the neural network and the symbolic reasoning, and try to overcome the shortcomings of both architectures. So I was wondering whether your principle-based AI is similar as the neurosymbolic AI, or it's a totally different concept.
So everything is related, right? But the principles are supposed to be substrates independent. So the principles are supposed to apply to a robot, to a cockatoo, to a human, and to an alien, even though we don't know what aliens look like, right? They're supposed to capture really what it means to be intelligent, irrespective of how it's implemented. So to use a principle, you need to still take it and implement it, right? You need to instantiate. That's what a principle is. It needs to be instantiated. So, in neurosymbolic computation, you're using a particular assumption about the substrate, and yes, you can implement these principles in that substrate, and maybe some principles are really easy to implement in that substrate, and then you would want to use that, right? So, but the short answer is I think these principles are above any specific implementation.
The thing is that people are studying the learnability of the new symbolic AI, because back propagation it's a differentiable, so people can propagate the errors. But for the principles, I think it's quite difficult to get this differentiable characteristics.
Yes. So the one principle that I was talking about that won the best paper award is basically based on back propagation, just not in neural networks. In a network that is not neurally inspired, that has a higher level semantic than what a neuron can do. But effectively, the way to generate actions is back propagation, nothing else. So it's super simple.
Okay, thanks.
Thank you.
Thank you, Oliver. Yeah, we're going to come to the next talk in this line. It's going to be Benjamin Kuipers. Hi, Ben. So you can see me. He's going to be. It's going to be a remote talk. He didn't have a chance to come here, but Benjamin is an amazing colleague and researcher I know for many, many years, and he's actually an emeritus professor for electrical engineering and computer science at the University of Michigan, where he, before of that, was professor for computer science and engineering, and he was also before that an endowed professor in computer science at University of Texas, Austin. He is a fellow of the AAAI, IEEE, and AAAS. He got his bachelor's from Swarthmouth and the PhD from MIT. He does research in AI and focuses on representation, learning, and use of foundational domains of knowledge, including knowledge of space, dynamical change, objects, and actions. I first got to know him reading this paper, The Semantic Spatial Hierarchy. It was actually one of the very first works that combined navigation and geometry with semantics. Back in the days, it was actually a pretty pioneering work, and currently is working also in the space of ethics and as a foundational domain of knowledge for robots and other AIs that might act as members of the human society. Benjamin, it's a pleasure to have you here, even remotely. I would prefer to have you in person. My conversations with him have always been very, very inspiring, and I'm looking forward to your talk.
Thank you very much. I just want to make sure that this is actually working. Good. I'd like to thank Oliver for his wonderful talk, and I'd like to build on it in a variety of ways. I agree very fundamentally with the stuff that Oliver talked about. So this, let's see, I should have, there we go, okay. It takes a little while for the change of slide to propagate to where I see it. As Wolfram said, I've been working in AI for a long time now. And part of it was at Swarthmore, part of it was at MIT. And it's all driven by the sense that AI is one of the great scientific revolutions to help us understand the mind. And so I ended up having to focus, of course. That's much too big a problem. So I focused on what I call foundational domains of common sense knowledge. And common sense requires being able to reason effectively with incomplete knowledge. And so I've worked in a number of these foundational domains to try to understand each of them individually and their common properties. But for this purpose, I'm going to focus on two of them. The foundational domain of navigational space, sometimes called the cognitive map. And then I've looked at several other domains about physical common sense, but then social common sense is also extremely important, and I believe that ethics needs to be considered as a domain of common sense knowledge. Now, we're talking here about the problem of embodied AI, and the difficulty of the problem of being embodied and being embedded in a large world, as Oliver was pointing out, is that the world is infinitely complex. And we humans have only limited resources for perception, representation, reasoning, acting, doing all of that. And if we take the notion of building embodied AI seriously, it faces similar limitations. Its limitations may not be identical to the limitations that humans have, or fish, or raccoons, or pigeons, but they all have substantial limitations, and we have to cope. So how can this possibly be possible? Well, it's pretty straightforward, and we do it all the time. We build simplified models. These are the things that Oliver called small worlds, but in fact, I believe they should be considered models of aspects of the complicated world. So yeah, engineers and scientists use models all the time, but we also use them in common sense knowledge. So a model picks out a small set of elements and relations among those elements. These are the known unknowns, the things that we can reason with. But necessarily it omits the everything else, the unbounded amounts of everything else, and treats it as negligible. Now, I pick the word negligible on purpose. Those other things, it's not that they don't exist. it's that they can be neglected for the purpose of this model. And so we might call those the unknown unknowns. They are the things that are effectively invisible to the models that we're trying to use. So as I mentioned, scientists and engineers use carefully selected models. They test their limits, figure out how to apply them. Common sense knowledge is a way of using a bunch of carefully selected models, optimized to use incomplete knowledge, which is what we always have, and use it effectively. So sometimes it's a matter of picking out a particular useful model. Sometimes we solve a problem by using one model for part of it and then another model for something else. But this is dangerous because, and the danger comes from the unknown unknowns. We can leave out something that's actually turned out to be important. We can look at a model, we can say everything in this model looks correct, and we're applying correct inference in mathematics. Why does it give us a bad answer? Because something that turns out to be important in the world is actually invisible in the model. So if that happens to your model, then it can lead you to making a bad decision, even when you appear to be doing everything right. So back in the day, once I decided to look at the problem of intelligence and the way AI helped us get leverage on the mind, I sort of look around and I see what people are thinking about, and there's lots and lots of really interesting, really hard problems under perception, thinking, acting. As Moravec pointed out, we make a lot of progress in the thinking category, and we have a whole lot of trouble, in the past anyway, handling the perception and action parts that even a toddler can handle pretty effectively. But when I was thinking about this, I realized that what I thought was the important part was common sense knowledge within this thinking part. And there were lots of other smart people working on those other things, so I'll focus on common sense. Well, that too divides into a bunch of different categories of knowledge. And so some of that is common sense about the physical world, where I am one agent inside a world and I want to understand that world. But in the social world, I am one among many agents, and I need to understand other agents. I need to understand how I can learn from them. I need to understand what I can do in order to interact with them. So I'm going to start out by looking at navigational space, because that's actually where I started a long time ago. So here's the tech report that represented my, that reprinted my PhD thesis. And this is obviously from about 1,000 years ago. The cartoon on the cover sort of illustrates the fact that different people have different knowledge of the same thing. And one of the things that goes on is that an expert here on the left can give you an explanation, and the listener on the right can make a total hash of it. But it actually makes pretty much sense for a little while before it deteriorates into confusion. So, starting with what I did for my PhD thesis, and then learning a bunch of important things about control theory, my group and I came up with this thing called the spatial semantic hierarchy that Wolfram already talked about. And so this lays out several of the important models that make up the spatial semantic hierarchy. And they can be categorized as qualitative and quantitative, and continuous and analog on the quantitative side. But they also are sensory information, control laws, causal effects of actions, topological models of the world, and then finally, which Wolfram and his friends got around to doing really well, the global two-dimensional geometry. One key notion in this is the concept of a distinctive state, which is a way of representing what you converge to in the basin of attraction of a hill climbing control law. And it gives you a kind of primitive for traveling through the environment. If we see that X on the left is one distinctive state, and I follow a control law corresponding to the action A over to the right, it doesn't have to get me exactly to my destination, X prime. It just has to get me into the basin of attraction. And then hill climbing brings me to X prime. And there would be corresponding control laws and for travel and for hill climbing on the left. That pattern of behavior can be abstracted from pixel level interaction with sensory readings to a very simple causal control law. If I'm at X, A takes me to X prime. If I'm at X prime, A takes me back to X. And so what this does is it takes me from one model, the control model, to a different model that is more concise, but also that abstracts away certain things. And so this is a video that shows, this is a real robot. It's a trace from the sensory data of a real robot exploring an environment at the University of Texas, actually. And while it's doing this, it's building the topological map that's portrayed on the right. And I could go into some detail about those things that you're seeing projected, but it's taking very high volume experience, sensory experience in the world, and creating a very low information topological representation of the world. And so my claim is that in order to deal with navigational space, you have to deal with both of those models, actually all of the models that you saw in that earlier diagram. Well, all of them is actually not quite right because, in fact, there's a lot of variation among people, as we saw in the original, in that original cartoon. And many people can navigate effectively even without the full supply of models. So this was another environment where a simulated robot investigated this environment, finding distinctive states to link control laws into a much more simple finite graph that represents the structure of the space. So what happens for navigational space is that the spatial semantic hierarchy builds multiple models. And so we have local geometry, local control laws, local topology, and global geometry. And an interesting fact is that you don't need them all, but you need to, they have dependencies, so you build up from the bottom. And so what these are is a set of simple, concise models, and individually and together, they make effective use of incomplete knowledge. The important thing, both for an individual learning this knowledge and for scientists investigating it, is to understand the limits of each of those models and change as needed to other models. And so the way the overall spatial semantic hierarchy gets created is that people learn at one level and abstract information that can help create the model at the next level. So looking at this agenda for common sense knowledge, what we see is that navigational space is kind of fundamental to an awful lot of things. Furthermore, this representation for knowledge has been refined and improved over the millennia, over millions of years by biological and cultural evolution. Navigational space is a really good example for finding very sophisticated levels of intelligence in non-human biological organisms. And to see where it exists in other creatures and where it doesn't exist is an absolutely fascinating thing. So now what I'm going to do is shift gears a bit and switch to the social world, where I'm going to talk about ethics. And ethics may seem like a big jump from the cognitive map, from navigational space, but it seems to follow somewhat the same functional role for an agent. The cognitive map says, if I need to get from here to there, how do I do it? How do I find and follow a path that will get me from A to B? Part of what ethics does is say, I can make plans to get from my initial state to my goal, but what's okay to do? Which plans should I do? Which plans should I not do? How do I make that decision? And in particular, what models do we use in order to make decisions like that? So part of what this requires is thinking about individuals and societies, because individuals are the members of societies, and it's individuals who have goals and who make decisions about how to act to make progress towards their goals. And they make those decisions based on the world as they understand it to be. And it may not be the world as it actually is, but it's the world as they understand it to be. A lot of that information comes from sensors, but a lot of that information comes from various kinds of inference. The theory of mind is an area in developmental psychology and in philosophy, but that spends a lot of time on that. One of the kinds of mathematics that we can call on for this kind of work are various models of rational decision-making, particularly game theory. Now, game theory is inspired by recreational games, which are typically zero-sum games, and they formulate decisions in terms of states, actions, transitions, the probability of those transitions, and utility functions that express your preference for a particular state. Now, if this sounds a little like the graph I showed you in the cognitive map, that is an interesting and important structural similarity. And then within the game theory model, we select actions in order to maximize utility. It's all straightforward. There are straightforward algorithms for doing this. People make quite a good living working on this stuff. One of the concepts that I'm going to point out is particularly important from game theory is the distinction between positive sum games, negative sum games, and zero-sum games. Recreational games tend to be zero-sum. Let me go back a bit. If a society is made up of people who primarily are interacting in positive sum ways, then the society will become more prosperous over time. Now, what I want to do first is spend a little bit of time going into detail with a favorite game that a lot of people know. You probably all are familiar with this, but maybe not with the interpretation I'm going to give it. And that is The Prisoner's Dilemma. Now, the actual prisoner story tends to distract people because the rewards are all negative. So I'm restating it in terms of positive rewards. So we've got two players. They're working together for obtaining rewards, but they've been separated so they can't communicate with each other. But if you and your partner cooperate, so each of you decides to cooperate with the other, then you each get a reward of 3. Is this dollars, gold bars? Doesn't matter, whatever it is. On the other hand, if you decide to defect while your partner cooperates, you get 5 and your partner gets 0. And if both of you defect, then you both get 1. Okay? So this is the payoff matrix. So your decision is the one on the left, your partner's decision is the one across the top, and these are the payoffs for you and for your partner. And what's really bizarre about this is that whatever your partner does, defecting is your best choice. So if your partner cooperates, you either get 3 for cooperating or 5 for defecting. So it seems like a good idea to defect. If your partner is going to defect, you're better off defecting. So your choice is clear. You better defect. But your partner faces the same decision, and so the result is that both of you defect, and the payoff is the worst one available collectively. You get 2 when you had other options for getting 5 or 6. How can you, this is supposed to be a utility maximizing algorithm. If the utility maximizing algorithm gives you the worst outcome, what's wrong? The cooperative solution is obviously better. Now, in game theory, it's not a Nash equilibrium. It actually requires trust of your partner, and your partner needs to trust you, and you both need to be trustworthy. But these terms are not included in the model, so they are invisible. These are unknown unknowns. We've got a model that includes certain things. When you do your inference within that simple world model, you get the choice that we've seen, and it's a bad one. So naturally, cognitive psychologists, social psychologists, have run these with human subjects a lot. And when humans play these games, they, on average, tend to use better models, things that make more sense to humans, and they make better choices and get better rewards. Except for majors in business and economics. There's a surprise, huh? So you should go back, chase down this paper. People who have been taught game theory, they end up buying this simple-minded model and not being skeptical of it, and producing a recommendation that exploits the vulnerability of their partner. Now, I talked earlier about society and how important cooperation is for society. So cooperation is positive sum interaction among the individuals in society. Society prospers when individuals cooperate. But cooperation involves vulnerability. And the vulnerability requires trust. And trust is valuable when your partner is trustworthy. But if your partner is not trustworthy, then you get exploited. This is the conclusion that you need to draw from the prisoner's dilemma. So what is ethics? We got started with this saying, how does society use ethics in order to get a better outcome? Well, my claim here is that ethics is how a society teaches its members three things: how to be trustworthy, how to signal that you are trustworthy, and how to recognize whether others are trustworthy. And there's a bunch of characteristics to look at. Now, this fits into a framework, an evolutionary framework for the evolution of society. Now, that depends on a number of different factors, just like biological evolution does. Now, okay, and one of those is how well the ethics of the society encourages positive sum outcomes. And the other part of the ethical picture is how well the ethical beliefs are transmitted to new generations. Now, I'm not going to go to that second one, but how well ethics encourages positive sum outcomes is important here. So here's an example of utilitarian decision making. Here you're in a situation, you're facing two options, A and B. What should you do? Well, it's pretty obvious. You should choose the greater good or the lesser harm, depending on whether they're good or bad. That's pretty straightforward. That's how utilitarianism works. Well, the trolley problem, and it's been transposed into the autonomous vehicle domain, says, suppose you're traveling too fast on a narrow road and a pedestrian suddenly appears and you have only two choices. You can either kill the pedestrian or you can crash into a barrier and kill the passenger. What a terrible thing. Two bad choices. What are you going to do? And people have studied this, but it's the wrong decision. The actual decision, it's a model that's oversimplified. The actual decision was the one where you turned into that road and decided to keep going too fast. That there was an upstream decision point, and at that decision point, there was an option to do something that would have avoided the deadly dilemma entirely. So if A and B are both very negative, then before you make the decision between them, the point that I label AB is already very, very negative. And so its utility is far lower than the utility of going slower, and so that's obviously what you need to do. Now, people complain, well, how can you go back in time? Here I am driving too fast, somebody appears, what am I going to do? And the answer is, you're in deep trouble. But the teacher, the student, and the programmer of an autonomous vehicle have a responsibility to look forward in time, to anticipate deadly dilemmas like this. Sometimes you learn from a near miss. Sometimes someone else has a terrible, terrible experience and you learn from that. Counterfactual reasoning is critically important for this. Then you need to search for the upstream decision point. And I have to say, there's no guarantee that that exists. But in a lot of situations, it does. And you need to learn to recognize that decision point and what to do at that decision point. Now, turns out Aristotle knew all this. That you need to learn to use the right model for a situation. And Aristotle said that ethics is a skill just like carpentry. He called it practical wisdom. The Greek word is phronesis. You can impress your philosopher friends by showing them you know that. When you have this skill to make these practical decisions, the tough choices you face are fewer. That is, you avoid the deadly decision, the deadly dilemma, instead of confronting it. And so the questions to ask are, does the utility measure include what's important, like we saw in the prisoner's dilemma? It did not. Does the structure include the right decision point, like in the deadly dilemma, where it did not? Does this exhaust everything you need to know? Almost certainly not. But using the wrong simplified model for the complex world leads to ethical failure. And that leads to societal failure. So we get embodied AI, which faces the unbounded complexity of the world. In order to deal with that, simplified models are necessary, but we already know that simplified models are dangerous. Tough luck. You have to do it. AI agents that we are designing and building, they live within human society. That human society is as unboundedly complex as the physical world. Agents need to have common sense knowledge of the physical world and the social world, and that includes knowledge of ethics. So, my claim is that in order to do embodied AI, we have to understand common sense knowledge. That contributes to this much larger set of knowledge that we need in order to do embodied AI. And I have a bunch of recommended readings here. These books have all been very influential to me, and I've got a bunch of papers that I've written that I want you to read. Thank you. I think I have time left for some questions.
Are there any questions here in the audience? Anyone? So while everyone thinks about it, there's one over there.
Thank you for the very excellent talk. So my question is like, now we have a kind of very different type of models deployed to robot or autonomous driving cars. Some of them are more like modularized, okay, you need to detect traffic lines, you need to detect, like traffic light and etc. So you actually somehow understand where it fails, right? At least you can track back, okay, have you missed the traffic light? But there are also another stream which try to do this end-to-end with you feed enough data, you teach how to drive in the end. I mean, it's very hard to know why it fails, right? It will fail, but in your opinion, in order to make this more like ethical, let's say the model in the end also know how human behaves, which type of model in the end it will be the, let's say, easier for human to understand or to embed the ethical, let's say the norms of the society into the model.
Okay, as you saw with the spatial semantic hierarchy, there are many models, and you need to use many models at the same time. So one question, let's see, I need to make my thing. A good example that might illustrate this is what happened with the Cruise autonomous car a number of, I think it's now several years ago, when a pedestrian was struck by a human-driven car and thrown in the way of the autonomous car. The autonomous car hit it, but then lost track of where that pedestrian was. And and then it knew that one of the things that it said is it needed to move out of the traffic lane and move over to the side. And so it did that and dragged the pedestrian. The pedestrian has survived. Cruise has not. Now, the critical problem with the model is that they built the model so that it recognized that the pedestrian was involved in an accident. But then it lost track of the pedestrian. It didn't know where the pedestrian was, and it made a decision about how to move. Now, a human driver would recognize that it didn't know where the pedestrian was, and that there was a possibility that it could be doing damage by moving the car. And so it's important to include an aspect of understanding the situation better in order to make the right decision. And so here too, the autonomous vehicle made a bad decision because something important was invisible to it. And so as we figure out it's not that there is one model that allows you to put in ethical constraints. It's that you have to have many models that are running all at the same time, and that and you select among them the ones that you need to pay attention to for the current purpose.
Another maybe following up question, that how do you I mean, if you compare human to human, right, the trust we build up also based on, let's say, the heuristics, the numbers. Let's say if you know someone able to drive, and let's say in hundreds drive, maybe have one or few accidents. So there's this statistic we seem to believe it, right? And why? I mean, if you consider today's machine, some of the machine is already way better. Let's say some of the autonomous driving car, they have way less accident, but we still don't think they are safer, right? So is there something fundamentally missing, or it's need time that we get used to it, then we accept it, okay, this is already safe based on the statistic, we just trust the statistics? Or it's just the number statistic, or there's something like very different from human to machine, human to human?
No, I think that we need to understand more about what allows humans to trust and to allow humans to be willing to accept risk. An interesting example is people are often very confident about driving a car. And many people are very nervous about flying in an airplane. And flying in an airplane is actually much safer than driving in a car. But the control that you as the individual have over the challenges that might arise is very, very different when you're in a car from when you're in an airplane. And so that's a factor that makes a huge difference in what people find acceptable. And so if you have embodied AI that may, for some completely incomprehensible reason, just drive over a pedestrian, then that's going to be horrifyingly unacceptable, regardless of what the statistics say. People find that sort of thing completely fearful.
Explanation, yes, thank you.
Yeah. So I also do have a question for you, Ben. So how do you think we will be able to implement these trustworthy agents, or agents that can identify as to whether they can trust us? And how can we implement these ethical rules from your perspective?
Well, I do think that ethics is a critical domain of incomplete knowledge. And let me just see if I have a particularly good yeah. So I think what needs to happen is we need a collection of models, a little bit like the collection that I showed for the spatial semantic hierarchy, but a collection of models that are good for the variety of different ethical decisions that people need to face. And so I showed you two of them. One is the prisoner's dilemma, where you needed to say the model was incomplete because something important was left out of the utility measure. In the deadly dilemma case here, the model was incomplete because it didn't include the critical upstream decision point. And when acting in this domain, you need to be considering those upstream decision points. Now, how many more of those models are there? Well, we don't know. And so I think part of the research enterprise is to go and explore this. Now, there's another part which I didn't make a slide for, which is, let's see. I think it's the evolutionary part. I guess I did that before this. Yeah. We need to have models that help us make trustworthy decisions. But we also, and I talked about utilitarianism. Utilitarianism is very attractive to people in technological domains because it's a very quantitative, equation and algorithm oriented type of reasoning. But it's actually not very good for teaching ethics to new generations. And one of the things we need are some of the other approaches to formalizing ethics. And these are formalizing it in terms of the virtues that you expect an agent to demonstrate and the duties, the obligations and prohibitions that you expect a person to follow. And there are additional things, the contractual agreements that people need to follow and the care that they need to exert towards other people. So there are a variety of different models that are much better than utilitarianism for conveying and training new generations. And so all of these are part of how we make our society evolve in a positive direction.
Thanks a lot. Thank you, Ben. Thank you for your very insightful talk. Big applause from the audience. Thanks for joining. We would have loved to have you here, but I guess we will see you soon in the future.
Yes, I am sorry not to be there.
Thank you. We are going to continue from here to the last presentation of today. It will be given by Tamim Asfour. Tamim is a full professor at the Institute for Anthropomatics and Robotics at the Karlsruhe Institute of Technology, KIT. He is heading the chair of humanoid robot systems and head of the high performance humanoid technologies lab. He's actually one of the few professors in Germany who build actual humanoid robots, and he is known for his series of armor robots. He also has done a lot of work in the context of robot learning, imitation learning, programming by demonstration. He's well known in the scientific space. He is also head of the Robotics Institute Germany, the largest robotics project in Germany. And I'm very, very happy that Tamim is here today and speak about his research that he's been doing in the past and probably also things that are going to come soon. Thanks for coming.
Thank you. Yeah, thank you. Thank you very much, Wolfram. Thanks for the invitation. I'm really very happy to be here, and I'm working on humanoid robotics. Actually, this is what I haven't done anything else in my life, you know. Started with my PhD building the first humanoid robot, and I'm still doing the same thing. But as you know, this is, of course, a big and huge hype today. Humanoid robots, everybody is talking about that, not only in research, but also big companies in different countries, especially in the US and in China. And I think our motivation when we study humanoids or when we conduct research on humanoids is to build multi-purpose machines, machines which should be able at some point in time to perform any task what a human can do, and maybe even better, yeah, better than a human. And this is what we are interested in. We are interested, I mean, the workshop is about embodied intelligence. Many people talk about physical intelligence these days, and this is the next revolution or the next step, actually. How can we combine this digital intelligence, what we experience today, with the physical world? How can we bring things together in order to build these multi-purpose machines which are able to perform any task what a human can do? And I hope and I think our goal is to develop technologies to improve the quality of life of people, to empower humans. And actually, I added since few weeks the last bullet point on this slide, which I have been using since more than 20 years. Yeah. So humanoid robotics, according to many projections, is a multi-trillion market. Yeah. So there are projections which tell us that humanoid robotics in year 2035, the market for humanoid robotics, the capital market for humanoid robotics, will be as big as the market of automotive. And we know about all these goals what the humanoid robotic community stated that in 2050, a humanoid robotic team will win against the world championship. So, but where we are actually, I mean, we see so many things these days happening, yeah, we have to be careful, and this is an important message actually from my side today. We have to be careful when watching YouTube videos where many companies and people, sometimes unfortunately also labs, post actually videos about progress in humanoid robotics, what they are able to achieve, but we have to be very careful. This is still very far away from application in the real world. So this is what we are doing in my group actually. Let me go a little bit back. So we are working on the design of these robots from scratch. I call it the robotronics of humanoids. We are working in particular on grasping and manipulation and learning from human observation. And very important from my point of view is how to build systems not only from hardware perspective, but how to combine hardware with software architectures so that we have complete systems similar to our computers or similar to other appliances or to other products actually which are used these days. The applications or the target domains, in particular assistance robotics for household robotics, as you will see soon, and collaborative robotics, for example, for maintenance and repair tasks. So, and these are the robots what Wolfram mentioned. Actually, we are now finished the 7th generation of the ARMA robot. So the first one I started in '99 when I started my PhD. And now the 7th generation. And since we are focusing on grasping and manipulation, we build also hands. You see here all these hands what we have developed in the last years. And this is, everything is made really in the lab. So there is no component what we buy. Of course, we buy the motors, we buy the cameras, we buy the NVIDIA computers, whatever. But the design of these systems and the electronics is really made by my team or in the lab. And I structured the talk in 2 ways. So I will show you some examples about our research at home. So in particular, talking about what robots can do these days, or our robots can do in our kitchens. Yeah, this is very important. Yeah, not in every kitchen. In terms of grasping manipulation, learning from human and interaction. Yeah, actually we can load dishwashers since the 3rd of February 2008. This is a wrong statement. I can load my dishwasher in my kitchen in Karlsruhe since the 3rd of February in 2008. But I cannot load and unload Wolfram's dishwasher. Or my robot, I mean, when I say I, it's my robot. You understand what I mean. But this is actually exciting. 2008, we were able to demonstrate these tasks, and many colleagues here are aware of that and have seen that so many times in our kitchen. And you see here on the other side, first steps towards transferability of these skills to other kitchens is we move to another building, and this is another kitchen here where you see the robot is always, of course, it required a little bit of time, few weeks of time to adapt all these skills and so on to the other kitchen. But what you see actually in this video here, you see how natural language instructions like Amma, please help me to prepare dinner for 2 people are mapped into sensory motor actions. Yeah, like we have to understand, this is before the era of large language models and ChatGPT and so on, that preparing dinner for 2 people requires 2 cups, 2 plates, 2 chairs. The robot can reason about missing objects in a plan, like the salad bowl, which does not exist here in the environment, and where the robot, based on objects with similar affordances, replaced the salad bowl by the orange mixing bowl, what you have seen maybe before in the video. And in the meantime, we, as I mentioned, we developed the AMA 7 robot, and you see here some examples of the capabilities of these robots. These videos are sped up by 2 here, like manipulating deformables, like recognition of the intention of the human in the context of handover, or recognition that the human is not actually interested in any interaction. The human asks, for example, for the milk, but the person is not interested in having the milk anymore, and where the robot has to reason, okay, I can place it again on the table. But also some basic capabilities what we need, like collision avoidance. Yeah, you see that the robot, despite disturbances induced by the human, it is actually always avoiding collisions with the door, with the object, and with obstacles in the environment. And I'm so happy that now the next step will be to test this robot. And I would say from scientific point of view, we are ready, actually. We are ready that somebody take this technology and bring it to the next level and produce robots which can be distributed and used in different domains. Here in a facility, in care facility domain, where we started planning the experiments which will be done in October to support caregivers, yeah? Like handing over drinks and so on, cleaning tables, setting up the table, and so on. So maybe this is one of my strengths, or the strengths of my group. We can build all these systems. Really, yeah, we can do it. Yeah, like the metal, the electronics, the software, and so on. And what's very important is really the software, and how can we integrate these systems in the software. And you see here, I started in 2005 looking into cognitive architectures. We know so many types of cognitive architectures in the literature, and different instantiations of architectures. I mean, by the end of the day, all of them are the same. There are different drawings, yeah, different boxes with different colors. But the main challenge is actually how we can represent things on semantic level and on sensory motor level. How can we learn and abstract from sensory motor experience, and how can we map natural language or semantic instructions like what I saw before to motor commands. And the latest version, what we developed, is actually a hybrid in the sense that it combines semantic and sensorimotor representations is memory-based, where we believe that memory is actually crucial and important for the mediation between the two levels. And we worked on the implementation of different types of long-term memory, in particular here, deep episodic memory, in order to encode experience of the robot and to recall these experience, or in order to be able to make predictions about next possible actions in a given situation, but also for human-robot interaction in order to verbalize the experience of a robot to humans, to externalize the experience of a robot to humans in natural language. Of course, a deep neural end-to-end architecture. You see here, we collect information. We collect here information about everything, actually, semantic information about the objects we grasp, the locations of the object, the tasks or the actions which are executed according to a plan, but also all sensory motor informations, like the images, the trajectories where the robot execute, the timestamps, and so on. We combine encoder-decoder architecture for symbolic, sub-symbolic information with the encoder-decoder for text and for speech. And in order to be able or to have a robot which is able to answer questions about its past. So, like, did you see the red cup? Yes, I saw it 10 minutes ago on the table, for example. And let me show you an implementation of that, a real implementation in.
Can you please tidy up while I'm away? All right.
So, can you tidy up while I'm away? Of course, the robot have a plan or knows how to clean the table here. It collects all the information about the objects, its grasp of the configuration of the arms when moving, where the objects were placed, how much forces actually were executed during a certain action. So multimodal information about all this tasks. And this is what we need actually for foundation models in robotics. We have to collect all this data.
Tell me what you did, please.
And now
the multivitamin juice to the countertop. How long did it take to grasp the green cup today in the afternoon? It took about 1 minute. Tell me which object you moved to the countertop yesterday at 2 p.m. I moved the red cup. When did you last see the red cup? I saw it on December 9th at 14:56.
So this is only one single example, one single experiment, actually. And now this is our dream, right? To have robots which collect data, collect experience, and learn from this data with large models, small models, large worlds, simple worlds, and so on. But if you think about it, actually, this robot, what you saw here in the demonstration or in the video, generates about 350 gigabyte data per hour. This is about 8 terabytes per day or 3 petabytes per year from only one single robot. And if we think about these visions of people to have robots distributed everywhere and they should share experience, upload their data somewhere, we train large models and we download all these skills. We download these skills to the robots. I think we don't have enough memory, in order to store this data. And this data is also significant if it is in the latent space. I don't have a solution. There are maybe other people here in the room, actually. We saw exciting talks today and who are experienced in how to do with these things. But we looked into actually forgetting in humans. So how humans actually, or what other disciplines like psychology tell us about forgetting mechanisms of humans. And we know that when we collect data, we have similar data is not important, actually. There are things in the data, what the robot experience or what we experience, that are irrelevant or redundant. And we implemented a first mechanism for forgetting in our episodic memory, as you see here, based on similarity of data, based on importance of data, or time decay strategy, or frequency of the use of the data. And we showed in an object search task that we can achieve the same accuracy in object search task with only 3% of the original data. We collected. Only 3% of the data which was collected was sufficient to have the same accuracy in object detection or object search task. So I will not go too much into details, but I will show you actually a little bit about the potential or the transformative impact of humanoids. So it's not only really about household robots. This would be my favorite task, but we were able here to demonstrate transferability of many of these things we developed in terms of systems and their capabilities to other domains. For example, here, repair and maintenance task, where you have complex manipulation, where you have to deal with failure. So how can robots learn from failure, where robots and humans have to collaborate together, for example, in a repair and maintenance task. Or in dangerous tasks like decontamination of nuclear plants, as you see here. And I will show you a few examples here. Here is another instantiation of our robot. This is the 6th generation. It's a little bit bigger because the task was repair and maintenance in warehouse environments, where this guard of the conveyor belt is about 20 to 40 kilograms, and therefore we had to build a robot which is able to carry actually 20 to 40 kilograms, what this robot can do with its arms and its hands. But the main goal here of the project with colleagues from Europe, this was a European project with Lourdes Agibato from London, Ud Billard, and Fiora Pirri from Roma, to develop a robot which is able to recognize when a human is in need of help based on different modalities, based on understanding of the task and the current situation, based on visual information, or direct natural language instructions, or based on haptic information when the human and the robot perform tasks jointly. And you see here some of the examples. I mean, these are really challenging tasks. And again, it's not just a video here. It's a video what we can demonstrate all the time. The videos on the top, they are accelerated by factor 2, and the videos on the bottom, they are actually with the normal speed. On the one hand, you see here the robot is guiding or navigating the cart and placing it somewhere. And on the other hand, the robot is placing the ladder for the technician in order to inspect the conveyor belt from the top. Another application, as I mentioned, decontamination tasks. This is a competence center of the German government, where you see here cleaning of contaminated objects is done by humans in contamination cells, and the idea is to investigate how much or whether robotic technology here is ready in terms of doing these tasks so that the humans can get better, meaningful jobs. Yeah? And what we are doing, my group is doing actually in this context, is grasping. I mean, these are parts which are in boxes, very cluttered, different shapes, different appearances. And we investigated here how we can apply methods from previous work using affordances of objects in a scene in order to generate grasping hypothesis in these cluttered scenes and to select the best grasping hypothesis either manually on the left or semi-autonomously in the middle or completely autonomous on the right. So the second part or area in our research is learning from humans. So we would like to make programming of these robots as intuitive as possible. Therefore, we're working on imitation learning, the idea of having a motion alphabet or a library of motion primitives, which we can use in order concatenate and use in order to solve complex tasks. You see here some early examples what we did here, but we are currently working in two directions. So the first one is to collect accurate whole body human motion data. This is here mock-up data, one of the biggest accurate motion databases worldwide, where we have not only the motion of the people performing these tasks, but also of the objects. So we're not aware actually of other motion databases with accurate data where also object information is considered, which is very important for manipulation. It's not only the motion of the human, but also the motion of the human and the objects the humans are interacting with. And you see here we can, with machine learning methods, segment all these motions in terms of, for example, on the right side, what every hand is doing, holding, placing, cleaning, whatever, or segment the poses of the human body in whole body local manipulation tasks as you see here. So, and what we are interested in, as I mentioned, to learn manipulation from a human demonstration, because I believe manipulation is the grand challenge, not only in robotics, the grand challenge of intelligence. So, and therefore, in these examples, I mean, this is the goal, to learn these manipulation tasks from human observation. And as mentioned, manipulation is not only a grand challenge of robotics, but a grand challenge of intelligence, because manipulation is our ability to change the world. And Stephen Hawking actually said that intelligence is the ability to detect change and to adapt to that. So, and what I'm going to show you here is something what we did, where also following exciting concepts, actually, for example, from Oliver, he talked about environmental constraints and that we should exploit environmental constraints in order to build more efficient robot systems, or to come up with new paradigms, actually, towards more efficient programming or more intelligent behavior of robot systems. And if we look at manipulation in all these tasks here in breakfast preparation, manipulation is only about constraints. So, for example, here, all these things are bimanual constraints. The hands, they have to fulfill certain spatial constraints, like you are on the top of the mixing bowl, so that you can pour something, or when you mix, there are the one hand is dominant, for example, the other hand, which provide the reference frame for the other hand, or when we carry objects with two hands, these are force constraints between the two objects. And our aim and our goal is really to describe manipulation, in particular here, bimanual manipulation tasks, in terms of constraints, in a constraint space. And the question is now, how can we actually detect constraints, and how can we formulate them, and how can we use them for control and for learning? And in the context of bimanual manipulation, we developed a taxonomy. I mean, we know taxonomies, they have their advantages and disadvantages, but they contributed a lot to our understanding and progress in grasping. And this is the first taxonomy we know, comprehensive taxonomy we know about bimanual manipulation, where we distinguish between coordinated and uncoordinated actions. And in particular, bimanual coordinated actions can be distinguished again on the second level, or we can distinguish between loosely coupled, where you only have temporal and spatial constraints. You would like to pour something into the cup, for example, or tightly coupled coordination, where we have force constraints, we have contact, actually. Forces applied on the one hand are transferred through the object to the other hand. And here we also have different roles for the hands. In symmetric tightly coupled manipulation, the hands move actually in a symmetric way, but we have also different roles for different hands in asymmetric actions where one hand is the dominant, for example, in a task. This sounds a little bit too complicated and a little bit artificial, but the goal is actually what people have been doing in programming by demonstration so far. They are segmenting human demonstrations and trying to learn primitives where the concatenation of the primitives lead to the goal of the task, right? But what we would like to do, I would like actually to describe human demonstrations as, and you see here we have different categories now of bimanual coordination, like loosely coupled coordination, tightly coupled, symmetric tightly coupled, asymmetric tightly coupled left dominant, asymmetric tightly coupled right dominant. So we have 7 categories of bimanual coordination patterns. And we would like to describe human demonstrations as sequences of these categories, not as sequences of primitives, what the right hand did or what the left hand did. But you see here in these tasks, we see here we start with loosely coupled, for example, and then we go to tightly coupled asymmetric right hand dominant, and so on. And why this is important, this is crucial and important, because if we know actually what's the category of coordination, then we know which controllers to trigger. Because tightly coupled asymmetric right-left dominant, these are actually, can be easily implemented by follow-a-leader mechanisms, what we know from control. We know actually which controller should be triggered for the left and for the right hand. But everything is done now with mockup data, and we would like to have robots actually which are able to extract these constraints in manipulation from human demonstration. And this is a recent work what we did where we are able to extract these constraints, geometric constraints between objects in manipulation only from video demonstrations, only from video data. And you see here this example on the left hand. If we think about the pouring task, actually, in different cups of different sizes and different shapes, because this is generalization, right? If we learn how to pour from the kettle into the cup, we would like to use this knowledge in order to pour from any kettle into any cup. But if you look at this, actually, you see that what's important here for the task is this reference frame here on the rim of the cup, and the points actually on the bottom of the cup of the kettle. And we know that these points, the bottom of the cup of the kettle, move along a curve, right? A trajectory. So in this case, for this pouring task, we have a point to curve constraints, which we should be able to extract and represent. And I mean, this is a very sparse representation. For the pouring task, I only need to really describe the relations between the reference frame on the rim of the cup and the bottom of the kettle. So, and what we do, we use pre-trained stable diffusion models and so on. I'm not going into the details here, where we can, we extract dense correspondences and candidate points from human demonstration for these important key points for the demonstration. These are the invariant task features. And you see here that we can extract these important key points from the demonstration, the constraints, and we can align different viewpoints in order to build these generalized representation. You see here, from 8 demonstrations here, we have the eight different positions here for the handle, and then we can extract the curve along which the handle here of the kettle move. And of course, the spot here is our reference frame, which is important for a successful execution. But we don't have only this type of constraint, right? I mean, we have many types of constraints. If you think about pressing a button, this is only actually a point-to-point constraint. Yeah, the tip of your fingertip and the bottom. These are the only things actually which should move together. But you see here, we have linear constraints which can easily be extracted based on principal component analysis, nonlinear constraints with principal manifold estimation, and of course we need the 6D pose of the object or of the reference frame for the rim of the cup, on the top of the cup. We evaluated that on 6 tasks here. You see here, press the button, fetch tissue, hang the hat, insert the stick, clean the table, and pour water. And you see here that these are the different constraints and the number of demonstrations which were needed to converge to the right or the final set of constraints for the task. And you see here, after 5 demonstrations, the first, in pressing the button, we converge here to a point-to-point constraint. The same here, hanging the hat, inserting the stick, or clean the table. And for pour water, as it is a nonlinear point-to-curve and point-to-point constraint, here you see that with 8 demonstrations, we are able to extract these constraints. And now, how to link the two things together? I motivated bimanual manipulation. And in bimanual manipulation, of course, we cannot use concepts like a master and slave object. When you manipulate an object with one arm or with one end effector, of course, the object is your slave and the end effector is the master. But in bimanual manipulation, you have multiple masters and multiple slaves, right? If the object for the right hand, the slave, is the knife, then it is the master, of course, for the cutting task. If you're interested in these details, you can read our paper at ICRA here. But based on human demonstration, actually, of bimanual task, we can automatically extract the type of bimanual coordination or the bimanual coordination category. For example, here in the pouring task, this is a loosely coupled bimanual manipulation because there are not forces actually exerted between the two hands in this case, so that we can trigger the appropriate controller and execute the task. You see here some evaluations. These are 8 demonstrations, taken video human demonstrations, and the execution on the robot for coordinated, tightly coupled, coordinated loosely and tightly coupled, uncoordinated bimanual actions, and uncoordinated unimanual actions. So, this is exciting actually, but these are, of course, results which work in a certain domain in my lab. Yeah, I'm not claiming that. Of course, the work was published in Transactional Robotics. Thanks a lot. This means something. This doesn't mean that this is really just yeah. It has a value. I hope so. At least few reviewers, so that this. But actually, the transferability of these results now to other domains, to other tasks, and to other robots is completely unanswered, right? We cannot say anything about that, and I expect if I start tomorrow now transferring this to a robot at a different space, a different place, that it will take maybe a month in order to get these things running, which is not okay for progress in robotics, right? And I think this is something we a little bit not good in doing it in robotics, that similar to a machine learning community or computer vision community, where they developed really tools where everybody can use on the fly in very easy way. But robotics is complex. Yeah, robotics is not like download of a data set and a Python script and then everything is there. Yeah. And we have to be aware of that robotics is complex compared to other domains like computer vision or machine learning. And on the other hand, we have, as roboticists, think about how we can actually provide better tools provide better tools to the next generation in robotics so that at some point maybe we have similar tools like in computer vision these days. So I believe the next revolution is embodied AI, physical AI. This means actually the fusion of robotics and AI. The challenges are on the first challenge from my point of view is really how to build these systems, how to engineer systems. I mean, until 2 years ago, actually, many groups were struggling in building 2 legs, right? 2-legged robots which can walk a little bit. In the last years, we made a lot of progress. If we look now to Unity and what others are doing, this is really a progress in terms of building these systems. But this is not the complete story. These are only legs which can balance and can walk, but we are not aware, at least I'm not aware, of any system which can do that and manipulate at the same time. So we need really platforms which work in the real world, and we are making some progress in terms of mechatronics in the last years. But we have also to think about the coupling between this mechatronics and the software, about building architectures which are transferable, reusable on different robots. In particular, for assistive robotics, they should be, of course, privacy aware, safe. Nobody is talking about safety in humanoid robotics, and also trustworthy systems. Of course, learning remains one of the biggest challenges. Yeah. From my perspective, engineering, I would like to emphasize that we still have to invest time and money and resources in finding ways how we can build robots similar to cars. Yeah. And of course, robot learning, I mean, this is a big challenge similar to human-robot interaction. And of course, societal aspects shouldn't be underestimated. And society is actually the most difficult part of the real world. Yeah. So we have to develop systems which are accepted by the society and machines what people actually want to have. Yeah. And machines which should lead to improvement of quality of life of people. Just a small example, what we are trying to do in Karlsruhe, we have what we call a real-world lab, where we conduct research together with society and with stakeholders. In this case here, in order to make artificial intelligence through our humanoid robots tangible or graspable to society and to stakeholders. Translated in simpler words, this means we are conducting experiments in different places of the city of Karlsruhe, in several kindergarten, at schools, at retirement homes, museum, and hospital, in order to get input how the new generations or the new robots, actually AI-based robots, should be, and what are the tasks what these robots should do. For example, in the nursing home, when you say, okay, you're developing assistant robots which should help elderly and so on, when we talked actually to the stakeholder, to the caregivers, they said, okay, it would be fantastic if you can build machines which save some of our time, of the caregiver time, like load the dishwasher, clean the table, bring a bottle of water to the room to Mr. X and Mr. Epsilon, so that the caregivers have time for the humans. And these are the things we are trying to do here and in this real world lab. And I think this is crucial and important if we want to have machines which are accepted, or robots, which intelligent robots which are accepted by humans. Yeah, I'm done. This is my team. These are the people, or this is the reason why I'm actually here in front of you, and I can present that. Without, of course, the team, we cannot do that. And of course, without the money, we cannot do that. Thanks to the funding agencies, and thank you for your attention.
Thank you, Tamim. Are there questions? This one.
Hi, Professor. Thank you for your wonderful presentation. I want to ask, in your demo, what is how many computation resource do you need it?
Sorry, how?
How much computation resource you needed, and where is the computation source is deployed? Is in the robot body, or in the edge, or in the cloud?
Yeah, thank you very much for the question. So actually, in all these videos, what I show, that all the computing resources are on the robot. So we have one very powerful GPU on the new robot for all these vision tasks, and but we have a LLM-based speech recognition system, which is not always used actually in this demo here, developed by a colleague of mine. And this is running on external GPU cluster. Yeah, but it's not really used in the dialogue management for the demos or for the tasks what we're doing here. But this is very important for us. We don't have any external sensors in the environment, and we don't need any. Of course, if we have more computer resources and can put on the robot, maybe we can do more things. Yeah, but currently everything is on board. The big problem actually we have is the energy, the battery, because if you have a GPU, a powerful GPU on your robot, the energy consumption is huge, and the batteries are always about 40 kilograms, actually, significant part of the weight of the robot, and these are things we have also to tackle somehow.
Further question? There's one over there.
Yeah, thank you a lot for the talk. So my first question is how close you think that the robot has to follow human body like structure? For instance, can you just for the power efficiency purpose, can you make like 4 fingers instead of 5? The degree of freedom has to be exactly like human, or actually it can be much simplified.
Yeah.
So that's
Yeah, for example, the hands here of these robots, they have only 2 motors actually. Yeah, and they are under-actuated hands. And some of the joints of this robot, they have continuous rotation. Yeah, they rotate 360 degrees without joint limits. But I still think that for these tasks, what humans are doing these days, this human-like morphology is the best. Also, when it comes to interaction with humans, so if the robots have to interact with a human and you know that the robot would behave like a human, I think the prediction of the actions of a robot would be easier for a human. I mean, this is a big debate whether the human-like morphology is the best morphology. At the DARPA Robotic Challenge, we know for the same set of tasks, different groups came up with different robots, like robots on 4 legs, where 2 legs can also function as arms in order to open doors and so on. I'm not aware of a better morphology, actually, and maybe for me it's not really important at this point. What's important for me, I don't want to change the environment for the benefit of a robot. Yeah, start putting cameras everywhere, for example, in the environment. Of course, we have some modern kitchens with IoT devices or intelligent kitchens, for example, where you can talk with the door of the fridge, and the door maybe opens automatically without exploiting environmental constraints. Yeah. I mean, if this is fine, if these environments are there, I think the tasks for the robot will be easy, but our environments are designed in such a way today, and we cannot start revising everything. Yeah. I'm not sure whether I answered now your question.
Perfect. So for the video you have demonstrated where the imitation learning in one of the last slides, how do you detect the human action? Like, do you have some computer vision key point detection, or is there some other teleoperation?
No. There is also no teleoperation, actually. We detect, I mean, we were using, for example, we're using the human body detector, open pose, yeah. Okay. And we are combining open pose with some additional mechanisms so that we can reconstruct the full pose of the body, yeah, in particular the hands, the end effectors of the human. And because the relation between the hands and the object in terms of 6D poses is very crucial and important for manipulation.
But do you think in the future that this can be really simplified, just like showing the videos and using computer vision is enough, or do we still need to have a more involved teleoperation method or system?
I mean, if we are able to really generate all these, for example, constraints from YouTube videos, we would have done it, you know. But the problem, the problem, you need really, as far as I know from computer vision point of view, that it's not really possible now in all these YouTube videos to generate all these constraints what we need, yeah. Maybe at some point. What I wish, if we have actually vision models or vision language models which are power efficient, yeah, and low energy, low power actually models which are implemented somewhere in hardware and implement certain capabilities, like for object detection, like for human tracking, and so on. I mean, if we have dedicated hardware components which solve some of these tasks, yeah. I mean, now we have, for example, a good human body tracker, and that somebody implement that in hardware, including whatever the NVIDIA Jetson, everything what we need, you know, the famous AI chips, but dedicated to some of the biggest problems in robotics, like object detection, human detection, and maybe think about how we can build hardware architectures based on this. I think we have to rethink a little bit how we are building our systems, because having only one GPU now is a big constraint for me to implement things on my robot, right? I mean, if we have people who start thinking about how a new architecture for a robot should look like, and in terms of capabilities which are implemented in hardware, like we have the whatever Huawei or NVIDIA chip for object detection, for 6D pose estimation, and concatenate these components in order to do, for example, vision-based grasping. Yeah.
Excellent. Yeah, thank you.
There's another question. And here's a microphone. You first or you first? Doesn't matter. You go ahead.
Okay, just ask a very simple question. So I was wondering whether the collaboration between the cloud and the edge is important from the compute point of view. So which kind of compute will be in the robot itself, or which computes that you have to do in the cloud or remotely, let's say, in a more powerful compute infrastructure? Do you think that it's important, or it's in the future that everything will be only on the robot itself?
It's very important. Actually, I wrote a proposal exactly on that we would like to have our robots collect all this data and stream it to a data center where all robots should learn from each other, and where you can download the new capabilities from this data center. The proposal was rejected, by the way, at a very early stage. So I think this is very important, but we need compute resources. I mean, robotics needs more compute resources than anybody else, than computer vision community, than speech community, machine learning community. Because the models we are talking about are, I mean, Wolfram is the expert here, are not only vision and not only speech, but vision, speech, motion trajectories, forces, whatever. I mean, and they are multimodal data, actually. And I think yeah, we need more than what's needed now, for example, for the speech or language models, right? But what we need in robotics, I don't think we can rely, at least to my best knowledge, about wireless communication now, or communication actually with external computer resources. We need things which are running on the robot. For the real-time parts, we cannot afford running whatever controller in the cloud, yeah. But maybe in the future, I mean, maybe if we have ultra fast communication, yeah, to cloud infrastructure, we can do it. But I'm not aware. But you are the experts here. Maybe you have some solutions we are not aware of, and I think this would be exciting actually. Because I don't think that we can have a humanoid robot at home with 3-4 GPUs of the current status of GPUs today, yeah? Only due to energy consumption, yeah?
Okay.
Hi, Tammy. So in the previous slides, you showed you asked the robot to prepare some meal for 2 people in the kitchen. And the tasks the robot performed there, how the task was trained? Were they trained purely on real data?
So this was actually done in 2018. This was classical symbolic planning.
Knowledge
really graph. Classical symbolic planning. No LLMs.
Knowledge
before,
graph,
yeah.
okay.
So, and this means, given this task, multi-agent, we have multi-agents and so on, and then a plan. This was a collaboration with a group of Mark Steedman in Edinburgh. And they generated a symbolic plan, and this symbolic plan was mapped to a state chart. I mean, the actions were implemented as state charts, which were triggered based on the symbolic representation.
Like a behavior tree. Something.
Exactly, like behavior tree. Yeah.
Thank you.
Yeah, since Wolfram already announced that I'm provocative.
Yes, go ahead. I know you.
Yeah. No, but I was struck by your statement that you think we need more compute and computer vision and large language models. And I'm struck by it in some sense because I think I will never have these resources available to me. And so, you know, that's scary because then I can't do robotics anymore. So you do humanoid robotics. So you're inspired by the human shape.
Mm-hmm.
And then why don't you extend that inspiration to the way the human works, which gets by with very little computation or energy?
Yeah.
And shouldn't we also try to solve that?
Oh yeah. I mean, our human brain. I mean, you mentioned that 20 watt, right? Yeah, we need only 20 watt for all this intelligence what we have. Yeah, but I think we don't know too much. I mean, I don't think that I will survive that in my life. Yeah, maybe my children, you know, that we understand how the human brain works. I mean, it's a kind of, yeah, brute force approach what I'm taking here, or what people are taking. Many people actually are taking. Very few people are thinking in the direction of how we can build brain-inspired architectures. There were some big projects like the Human Brain Project and so on, but still we don't know too much, I think, right? I mean, yes, we should. I mean, this would be fantastic, right? And this what I mean a little bit goes into the direction what I answered here. If we have now, if people start thinking about new computing architectures, really computing architectures for the capabilities what we need, like object detection, human tracking, speech recognition, and so on, and then build the machine which should process everything, and not take a von Neumann architecture and another one and another computer and a GPU cluster. I mean, this is a big issue, right?
Principles,
yeah.
There any further question? Yeah.
Yeah, it works. It works. Right. So, as you mentioned, that the robot have carried about 14 kilogram battery with it. So my question is, with this battery, how long will be this robot will be used?
About 2.5 hours.
2.5 hours?
2.5 hours. It depends actually how much the robot moves, yeah?
Okay.
So in this case, I mean, if the robot moves, then this is the highest energy consumption. Yeah, it's more than the GPU, whatever. Yeah. If the robot has to move all the time, then it has to, it needs energy to move 100 kilogram or
Yeah.
70. The new version is 70 kilogram, and the green one is about 120 kilogram. So you need a lot of energy to move 120 kilogram.
So, do you have some plan to reduce some power consumption to make the working time longer for this ARMOR series robot?
Yeah, actually, we worked with some colleagues from Embedded Systems Department or chair, where they developed mechanisms for energy power management system, actually, for the robot, similar to what we have in our computers, right? But as I told you, I mean, this reduces a little bit of the energy consumption of the computers. But if the robot moves a little bit, this energy of the computers is small compared to the energy which is needed for the motion.
Okay.
Yeah. So we need better, lighter batteries for sure. Yeah. And maybe also other materials so that the weight of our robots also is lower.
Okay. So, do you think this way is this way can be reduce power consumption? As some guy says that the brain of the robot, we call it the AI power, not in the robot itself, but in the cloud. That the network have a low latency. So the robot just do the things simply, but the brain is in the cloud. And do you think this is a way to reduce power consumption of the robot?
As I mentioned, we reduce the power consumption only of the computers, right? But the major power consumption is the power consumption of the motion of the robot itself, and not of the computer resources. If the robot is not doing anything all the time, like a template, then it's fine. But if the robot has to clean the table, to help people to stand up, to move around, then it doesn't reduce the energy. Your solution or your suggestion does not reduce really the energy. So we need really better batteries. I mean, this is crucial and important. And with the marathon now in China, I mean, this was one of the. I mean, the robots can walk for I don't know how many minutes, but then they had to again and again replace the batteries, right?
Actually, in China, for example, for the Unitree robot company, is the only can insist about 2 hours.
3 hours.
Yeah, 2 hours.
2 hours. Yeah.
Yes.
Yeah.
So here's one thing I would like to mention, that we saw today that get lots of exciting talks about like different types of modalities, and like adding to Oliver's comment, the question could be as to whether if we integrate all the modalities and really get into embodiment, as to whether then we will be actually much more efficient, because this is the hypothesis of the large language models, of foundation models, that they can actually generalize through the multimodal aspect. So it could be the case that if we really integrate all the modalities, then the learning will become much more efficient, and that we will need way less training than we are needing right now. But this may be something that we can discuss tonight during the dinner. Thank you, Tami, for this great talk.
Thanks again. Yeah.
So the dinner will be starting at 6 p.m. just across the hallway here. There's a restaurant. That's where the dinner will be. Thank you for coming today and for this exciting talk and the wonderful presentations. We will have further tomorrow morning. So Please don't stay up for too long tonight, and be ready tomorrow at 8:45 with a tea and a coffee whatsoever that you will be able to get here. Thank you.